For most of human history, we could only guess what the early universe looked like. We saw stars and galaxies nearby, but the beginning, the real beginning, was hidden in darkness. Then came the James Webb Space Telescope. Launched in 2021, it was built to see what no eye ever could. The first stars, the first galaxies, and the birth of everything we know. When it finally opened its golden mirror and looked deep into space, it found things no one expected. Galaxies too big, too bright, too early. Stars and black holes that shouldn't be there yet. It's as if the universe started moving faster than the rules allow. Let's explore what Webb saw, why it shocked scientists, and how its discoveries could change everything we thought we knew about the origin of the cosmos. Before Webb, why the universe's origins eluded us for so long. When our ancestors looked up and saw the stars, they had no idea how far away they were, how old they might be, or how the universe even began. When telescopes were invented, that changed everything. We could finally see galaxies far beyond our own. But even as our instruments improved, one big question remained out of reach. How did it all start? What did the very first galaxies look like? Astronomers spent decades chasing the earliest moments of the universe, trying to catch a glimpse of the first stars and galaxies that formed after the Big Bang. The idea was simple. If we could see far enough into space, we'd be looking back in time. Since light takes time to travel, looking deeper into space meant we were also looking into the past. But as simple as that idea was, doing it turned out to be far more difficult than anyone expected. The Hubble Space Telescope was one of the most powerful tools ever made for studying the universe. Launched in 1990, it opened a new window into the cosmos. Hubble showed us breathtaking images of galaxies, nebulae, and star clusters. It let astronomers look back billions of years. Some of the deepest images Hubble ever took showed galaxies that formed just a few 100 million years after the Big Bang. But even with all its power, Hubble had a limit. It could only see so far. The problem wasn't the telescope itself. It was the light from those first galaxies. The universe is expanding. That means galaxies are moving away from us, and the light they give off gets stretched as it travels. This stretching is called redshift. The farther away a galaxy is, the more its light is stretched. At extreme distances, this light stretches so much that it slips out of the visible range entirely. It becomes infrared. That's a type of light our eyes can't see. And while Hubble could detect some near-infrared light, it wasn't built to see the deep infrared. That meant the light from the very first galaxies, the ones closest to the birth of the universe, was completely invisible to it. This created a serious roadblock. We could guess what came before, based on what we saw later, but we couldn't witness it directly. Astronomers were stuck with a timeline that had a missing beginning. There was also the issue of how faint those early galaxies were. The first galaxies weren't large spirals like the Milky Way. They were small, messy, and dim. They didn't have billions of stars yet. Most of their stars were new, just beginning to form. The light they gave off wasn't strong to begin with, and after billions of years of travel, it grew even fainter. To see them, you'd need a telescope that was both sensitive to infrared and powerful enough to catch light that had been weakened by time and distance. That was something no telescope before Webb could do. Ground-based telescopes faced another problem too: Earth's atmosphere. It blocks much of the infrared light from space. So even if you built a powerful infrared telescope on Earth, much of the light from early galaxies would never reach it. Space telescopes like Hubble avoided the atmosphere problem, but Hubble's instruments simply weren't built for the kind of infrared work needed to spot the first galaxies. Some missions, like the Spitzer Space Telescope, were designed for infrared observation. But Spitzer was small. It didn't have the mirror size or the resolution to pick up extremely distant galaxies in high detail. It could detect heat, but not paint a sharp picture. All of this meant that, until recently, the earliest part of cosmic history remained just out of reach. We could estimate when the first galaxies formed. We could simulate them on computers. We could build models. But we couldn't see them. Not directly, not clearly. This gap in our view of the universe was known, and it bothered scientists for decades. We knew the Big Bang happened about 13.8 billion years ago. We knew that, hundreds of thousands of years later, the universe cooled enough for atoms to form. And then, after millions of years, the first stars were born. These stars grouped into the first galaxies. But how exactly did that happen? What did those early galaxies look like? Were they strange and chaotic or surprisingly structured? What kind of stars did they have? Could any of them host the conditions for early life? These were questions we couldn't answer without seeing them for ourselves. So scientists and engineers began working on a telescope that could go beyond Hubble, one that could see in deep infrared, one that could look back farther than ever before. It would need to be placed far from Earth, beyond the planet's heat and atmosphere. It would need a massive mirror to catch the faintest light in the universe. And it would need instruments that could stay cold enough to detect heat signals from the dawn of time. That vision became the James Webb Space Telescope, or JWST. The battle to launch Webb, engineering the coldest eye in space. Building JWST wasn't just a mission, it was a battle against time, against nature, and sometimes even against itself. The idea behind Webb was simple: build a telescope powerful enough to see the first galaxies. But turning that idea into reality took more than 2 decades of effort, trial, and error. It meant creating something that had never been built before: a cold, folding, gold-covered eye that could work perfectly 1,000,000 miles from Earth. The story began in the late 1990s, not long after Hubble had started revealing the deep universe. Scientists knew Hubble was limited when it came to infrared light. They needed something new, something colder, bigger, and more focused on heat instead of visible light. That's when plans for a next-generation space telescope began to form. It was originally called the Next Generation Space Telescope, and the goal was to launch it in 2007. But as the years went by, that goal slipped further and further out of reach. At the heart of JWST's design was its massive mirror. It would be more than 21 feet wide, much larger than Hubble's 8-foot mirror. But something that large couldn't just be put on a rocket as is. It was too big. So engineers had to make the mirror fold like origami. 18 hexagonal segments, each covered in a thin layer of gold, would fold up inside the rocket and then open once the telescope reached space. Getting that system to work was a challenge all on its own. The mirror had to unfold perfectly. Each segment had to align down to a tiny fraction of a human hair. Then came the sunshield. For Webb to see infrared light, it had to be cold, very cold, just a few dozen degrees above absolute zero. If any heat from the sun or Earth reached the telescope, it would overwhelm the faint signals from distant galaxies. So, Webb needed a giant sunshield the size of a tennis court. Not only would it block sunlight, it would also separate the hot and cold parts of the spacecraft. The sunshield had 5 layers, each thinner than a human hair, made of a material called capton. These layers would block heat like a series of umbrellas. But just like the mirror, the sunshield had to fold up for launch and then unfold perfectly in space. That required hundreds of pulleys, cables, motors, and springs, all of which had to work the first time. There would be no repair mission if something failed. JWST would be parked at a point called Lagrange 2 or L2, about 1,000,000 miles from Earth, too far for astronauts to fix. Each part of Webb's design was pushing the limits of what was possible. That meant delays were almost guaranteed. The original launch date moved from 2007 to 2011, then to 2013, 2015, 2018, 2019, and beyond. Every delay meant more testing, more redesigns, and more money. Costs rose from an early estimate of $1 billion to nearly $10 billion. Some in Congress called for the project to be cancelled, but others saw it as too important to give up. JWST had over 300 single points of failure, meaning if even one part didn't work, the whole telescope might not function. That's why testing took so long. Engineers had to simulate the cold of space, the vibrations of launch, and the unfolding of every part. In one test, a small fastener came loose and caused tears in the sunshield. The team had to stop everything and figure out how to fix it. In another, cables got caught during deployment tests, delaying the project even further. Even transporting JWST was a challenge. Its final assembly took place at Northrop Grumman's facility in California. From there, it had to be moved to a launch site in French Guiana, South America. But Webb couldn't be flown on a regular cargo plane. It was too sensitive. Instead, it traveled by boat through the Panama Canal, boxed in a custom-made container with special shock absorbers and climate control. When Webb finally arrived at the launch site, it was late 2021. Even then, the launch had to be pushed back again, first because of concerns with the rocket, then because of weather, and finally because of a small mechanical issue that triggered extra inspections. Each time, the tension grew. Years of work, billions of dollars, and the hopes of an entire generation of astronomers were riding on a single launch. The rocket that would carry Webb into space was an Ariane 5, one of the most reliable launch vehicles ever built. But even that didn't make people feel at ease. This was a one-shot mission. If anything went wrong, Webb wouldn't make it to its final destination. And if it didn't get there, it would never unfold, never see the early universe, and never send back a single image. On December 25, 2021, the Ariane 5 rocket finally lifted off and successfully carried JWST smoothly into space. But even then, the mission wasn't over. What followed was one of the most complex deployments ever attempted in space. Over the next month, Webb had to go through more than 300 steps to reach its final form. The sunshield had to unfold, slowly, layer by layer. The mirror segments had to open and lock into place. Each piece had to move in perfect harmony. Back on Earth, engineers and scientists watched every signal, every motor, every bolt. Each time something clicked into place, there was a small celebration. But no one breathed easy until the full deployment was done. Finally, in January 2022, Webb reached its orbit around the L2 point. The sunshield was fully deployed, the mirrors were aligned, and the telescope began to cool down to its operating temperature, just a few degrees above absolute zero. Even then, the work wasn't over. Engineers had to calibrate the instruments. They had to focus the mirrors so they worked as one. Each mirror segment could be adjusted with tiny motors on the back. These adjustments had to be precise, too much or too little, and the image would be blurry. Over weeks, they fine-tuned the system until the telescope was ready. It took over 25 years to get to that point. Years of setbacks, years of redesigns. But through it all, one goal remained the same: to see the universe as it had never been seen before. To go back to the very beginning and finally bring into view what had stayed hidden for so long. Parked beyond the moon, how L2 gave JWST its quiet place in the dark. The James Webb Space Telescope didn't just need a good mirror. It also needed the perfect place to sit in space, far from heat, light, and noise. It needed darkness, cold, and most of all, it needed stability. That place turned out to be nearly 1 million miles from Earth, in a quiet region of space known as L2. L2 is one of the few places in space where something can remain balanced in motion. It's part of a group of special spots in the solar system where gravity and motion work together just right. The concept of Lagrange points was first worked out in the 1700s by mathematicians who studied the way gravity works between orbiting bodies. There are 5 of these Lagrange points, and they all exist where the pull of Earth and the pull of the Sun cancel out in just the right way. At L2, the gravitational forces of Earth and the Sun balance with the motion of a satellite like Webb. That balance keeps JWST in line with Earth as both orbit the Sun. Instead of floating freely or circling Earth like the Hubble Space Telescope, Webb is parked in a kind of cosmic sweet spot. It doesn't orbit Earth. Instead, it orbits around L2 itself in a small, slow loop. This is called a halo orbit, and it keeps Webb circling a point in space. This gentle path ensures that the telescope always stays in the same relative position as Earth, trailing behind it like a shadow that never falls out of step. Being parked near L2 gives Webb a few big advantages. First, it lets the telescope keep Earth, the Moon and the Sun all on one side. That's incredibly important. All three of these objects give off heat and light. If the telescope were surrounded by them, or if they kept moving around it, their warmth would interfere with its instruments. But from its position beyond the Moon, Webb can point away from all of them. With Earth, Moon and Sun always behind it, the front of the telescope is free to stare into deep space with no bright or warm objects getting in the way. Since all the heat sources are in the same direction, the sunshield also only needs to block one side, making the overall design simpler. Another benefit is the steady temperature. Spacecraft that orbit Earth are always moving in and out of Earth's shadow. That means they heat up and cool down regularly, which can put stress on their parts. Webb doesn't have that problem. At L2, the sunlight is constant, but the shield blocks it completely. That means the telescope itself remains at a steady, deep cold. There are no hot-cold cycles, no shifts in temperature that could warp parts or confuse the sensors. Because Webb stays in a fixed position relative to the planet, it's always in contact with ground stations. There's no waiting for it to come around the other side of the planet. Every day, engineers on Earth can talk to JWST, send it commands, and receive data. This makes operations smoother and faster. Data from Webb's instruments can be sent back quickly, and problems, if they ever come up, can be addressed in real time. Reaching L2 wasn't easy. It took about a month for Webb to travel there after launch. The telescope didn't go in a straight line. Instead, it followed a careful, winding path, using tiny bursts from its thrusters to guide itself. These adjustments were needed because once Webb arrived, it couldn't stop and turn around. Even at L2, Webb isn't completely still. It loops gently around the L2 point in an orbit that takes about 6 months to complete. This orbit keeps the telescope from falling into the exact center of L2, which would be unstable. By circling around it, Webb stays safe and avoids drifting. This constant motion is predictable, and it allows JWST to maintain its careful balance of gravitational forces and momentum. Webb is about 4 times farther than the Moon. This puts it beyond most sources of interference. There's less light pollution, less radiation from Earth, and less chance of getting hit by stray particles or debris from satellites. It's not completely free from danger. Space is still full of micrometeoroids, but it's far enough away that the risk is much lower than in low Earth orbit. From Earth's orbit, telescopes can only see part of the sky at a time. They have to wait for the planet to turn or move. But from L2, Webb can see huge portions of the sky without waiting. It still has to shift its view now and then, depending on what part of the sky is pointing away from the sun, but it can keep its instruments on a target for days or even weeks at a time. That's important when looking at faint galaxies or distant stars, because long exposures are needed to collect enough light. L2 has been used before. Other spacecraft have visited the area, some for science, others for observation, but none have relied on it in the way Webb does. For Webb, L2 is a core part of the telescope's design. The instruments, the sunshield, the mirror alignment, all of it was built to function in this quiet corner of space. Without L2, the mission would not be possible. Not all Lagrange points are as stable as L2, which is just stable enough for a mission like Webb, especially with small course corrections, which are still necessary. Webb uses its thrusters from time to time to stay on track. These burns are tiny, just enough to nudge it back into place. They happen every few weeks, and they use a limited supply of fuel. Once that fuel runs out, Webb will no longer be able to hold its position. That will eventually mark the end of its mission. But engineers designed Webb to last for years, possibly longer than its planned lifespan. As long as the fuel holds and the systems remain healthy, Webb will keep watching the sky from its cold, quiet home beyond the Moon. The first deep field, a snapshot that broke cosmological expectations. On July 11, 2022, the James Webb Space Telescope released its first full-color image to the world. It was called the first deep field. It showed distant galaxies, some of the oldest and faintest ever seen, and it caught the scientific world off guard. This image was a peek into a part of the sky about the size of a grain of sand held at arm's length. But Webb's deep stare, which lasted about 12.5 hours, revealed galaxies, hundreds, even thousands of them, crammed into that little space. Bright spirals, red smudges, stretched arcs, and fuzzy clusters. There were galaxies behind galaxies, light bending through other light, and each tiny speck represented billions of stars. Astronomers had expected to see ancient galaxies, but they didn't expect them to look like this. The galaxies in Webb's deep field were more developed than they should have been. Some were too bright. Some had too much structure. In theory, galaxies in the early universe should have been small, messy, and dim. They were supposed to be just forming, chaotic clouds of gas and dust, with only a few stars coming together. But the galaxies in Webb's image weren't like that. They had clear shapes. Some were disks. Others were already forming spiral arms. And they weren't rare. There were too many of them, and they were showing up far earlier than expected. It was like finding cities where there should only be villages. This clashed with years of predictions about how fast galaxies should grow after the Big Bang. According to those ideas, there shouldn't have been enough time for galaxies like these to exist. Yet, there they were, fully visible, their light stretched into the infrared, captured clearly by Webb's mirror. Models had suggested the early universe would be emptier, with fewer galaxies spread far apart. But JWST showed a crowded sky, thick with ancient structures. That raised serious questions about how the universe behaved in its first billion years. Was it forming stars faster than we thought? Was matter clumping together earlier than models predicted? The brightness of some galaxies was another shock. A few were so bright, scientists wondered if they were looking at something else entirely, perhaps extremely active black holes or strange bursts of star formation. One galaxy in particular stood out. It was spotted in the first weeks of Webb's operations and appeared to be from just 300 million years after the Big Bang. If confirmed, it would be the oldest and most distant galaxy ever observed up to that point. And this galaxy seemed to hold almost as much mass as the Milky Way. To explain this, scientists began rethinking what they knew about galaxy formation. Maybe stars formed more efficiently in the early universe than anyone guessed. Maybe gas cooled and collapsed faster. Or perhaps something about dark matter was helping galaxies form quicker than expected. Some even suggested that parts of our cosmological models might need to be revised. Not completely replaced, but adjusted. There were also features in the image that weren't galaxies at all. Some of the bright arcs and strange curves were caused by a phenomenon called gravitational lensing. This happens when the light from distant galaxies passes through a massive object, like a cluster of galaxies in the foreground. The gravity from that cluster bends the light, magnifying it and stretching it into long curved shapes. Webb captured these effects with incredible clarity. In fact, the galaxy cluster that acted as a lens in the first deep field, called SMACS 0723, made it possible to see even farther into space. Some of the magnified galaxies behind it were too faint to be seen without this natural boost. JWST allowed astronomers to study these distorted galaxies in fine detail. They could measure their light, analyze their structure, and learn about their chemical makeup, all from galaxies that were otherwise invisible. It was like using a telescope on top of another telescope. This gave scientists a new way to look at the very beginning of galaxy formation. The image also revealed a wide range of colors, even though it was taken in infrared. Each color represented a different wavelength of light that had traveled across the universe. Scientists used filters to break this light into layers, allowing them to study the age and makeup of each galaxy. Redder colors usually meant the galaxy was older or farther away. Bluer shades meant it was younger or closer. By studying the colors, scientists could piece together a timeline of how galaxies grew and evolved over time. Many astronomers had waited their entire careers to see a picture like this. Some had worked on JWST for decades, never knowing if it would be launched, let alone succeed. And now, here it was, proof that their efforts had worked. An image showing what had always been out there, hidden, unreachable, waiting for the right set of eyes. Even people outside the science world could feel the weight of it. The photo became front-page news, trending online and filling screens around the globe. For many, it was the first time they truly saw how vast and full the universe is, that something so small, a patch of sky the size of a grain of sand, could hold so many galaxies, shook people's sense of scale, and that those galaxies were not just far away, but ancient, added to the wonder. Unexpected structures in the early universe, clumps, spirals, and bright monsters. Among the glowing shapes in those first deep images were galaxies with disks, curves, and even spirals. It was like walking into a construction site and seeing buildings already standing tall, finished, and detailed, when the blueprints suggested only foundations should be in place. One of the most surprising things was the discovery of spiral galaxies from this early time. These are galaxies with arms that twist outward in beautiful patterns, like pinwheels. In our part of the universe, spiral galaxies are common. The Milky Way is one. But spirals are also the result of time. They form slowly as stars settle into rotating disks and gravity pulls everything into shape. Seeing them in the young universe was unexpected. Some galaxies looked clumpy, but these clumps weren't random blobs. Many of them seemed to have structure, like star-forming regions arranged inside disks. Others were gathered into groups, hinting that clusters of galaxies may have been forming earlier than thought. There were signs of collisions too, galaxies crashing together, triggering bursts of star formation. Even the messier galaxies didn't seem as primitive as models had predicted. Some early galaxies were shining far more than expected. What was making them so bright? One idea is that these galaxies were forming stars at incredible rates, hundreds or even thousands of times faster than galaxies do today. Another idea is that they contained huge black holes that were pulling in matter and giving off energy. But that would mean that black holes were already large and powerful this early in time, which also doesn't match earlier beliefs. Some galaxies didn't match anything we see in the nearby universe. There were odd shapes, elongated forms, rings, and twisted arcs that didn't fit into familiar categories. A few of them were so dense and compact that they almost looked like stars, but their light signatures told a different story. These were entire galaxies packed into a small space, glowing fiercely from the inside. Some of the galaxies also appeared more mature than they should have been. Their stars looked old, even though the universe itself was still young. How could galaxies already have populations of older stars when only a few 100 million years had passed since the Big Bang? Stars take time to form, and larger stars burn out quickly, leaving behind signs that astronomers can detect. The light coming from these galaxies hinted at multiple generations of stars. That meant they had been forming stars even earlier than the images showed, possibly as soon as the universe allowed it. In some galaxies, scientists detected heavier elements, like oxygen, carbon, and even iron. These elements are created in the cores of stars and spread out when those stars explode. Finding them in ancient galaxies meant that the universe had already gone through a cycle of star birth and death, which again pointed to an earlier start for galaxy building. According to older models, such elements should have been rare or even missing in the earliest times. Yet they were there, glowing in Webb's data. Some of these ancient galaxies seem to have dust. Cosmic dust is made of tiny particles that form from supernova explosions and other violent events. Dust blocks visible light but lets infrared pass through. And the presence of dust so early in the universe means that stars had already lived and died, and done so in large numbers. Researchers began comparing the Webb results to earlier ideas from telescopes like Hubble. While Hubble had hinted at some of these surprises, JWST pulled back the curtain. The early universe was a fast, bustling workshop where stars and galaxies were forming rapidly and with more complexity than anyone had dared to expect. As more images came in, patterns began to emerge. There were hints of filaments, long thread-like shapes where galaxies were aligning. This pointed to the large-scale structure of the universe taking shape early, possibly guided by dark matter. Scientists had known that galaxies weren't randomly scattered. They form along invisible strands of matter, like dew along spider silk. But seeing signs of this so soon after the Big Bang meant that the structure of the universe, the cosmic web, may have formed quite early on as well. With each new deep image, more of these impossible galaxies showed up. Some were given nicknames. Others were flagged for follow-up studies. Each one brought new data, and with it, more questions. Were the early galaxies just different from today's? Had we misunderstood the timing of cosmic events? Or were there new rules at play in the young universe? Some researchers began to revisit the theories of early galaxy formation, adjusting timelines, changing assumptions, and questioning long-held ideas. There wasn't agreement on everything, but there was something else instead: excitement. The early universe was full of bright monsters and strange shapes, alive with energy, forming stars at breakneck speed and already rich with dust, gas, and the building blocks of future worlds. Did JWST break lambda CDM? For decades, astronomers have built their understanding of the universe around a model called lambda cold dark matter, or lambda CDM for short. It's been the backbone of nearly every idea about how the cosmos works, from the Big Bang to the way galaxies move and grow. Lambda CDM says that the universe began in a hot, dense state and has been expanding ever since. That expansion, mixed with the force of gravity from invisible dark matter, slowly pulled atoms together to form stars, galaxies, and clusters. The lambda part stands for dark energy, a kind of repulsive force that makes the universe expand faster over time. The cold dark matter part refers to a kind of heavy, slow-moving invisible matter that helps galaxies form by giving gravity something to grab onto. The model has worked well for a long time. It matches observations of the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. It fits the large-scale structure of the universe, the web of galaxies stretching across the sky. It explains how galaxies move, how clusters form, and even why the universe is accelerating as it expands. But JWST is now showing things that don't seem to fit. Structures are forming in timescales that were thought impossible. It's not just one or two odd galaxies. Webb's deep-field images are filled with them. If these galaxies are real and not measurement errors or misreadings of distance, then the lambda CDM model may need serious revision. That doesn't mean it's wrong in every way, but it could mean that something important is missing. Lambda CDM isn't just a single idea. It's a system built from many layers of theory and observation. Change one part, like how fast stars can form, and it might throw off everything else. That includes the way galaxies are distributed, how light bends around them, and even how the oldest starlight in the CMB looks today. Another idea is that there could be new types of particles or forces that we haven't discovered. Some physicists have suggested that dark matter might not be completely cold, that it might move a little faster or interact more than we think. That could help explain why galaxies formed so quickly in the early universe. But it would also require rewriting big parts of physics. Others wonder if dark energy, the lambda part of the model, was stronger or acted differently in the past. That might change the pace at which space expanded in those early years, allowing matter to gather more quickly. But again, there's no clear evidence for this yet, and it could make the rest of the model stop working in other areas. There's also the possibility that we're misunderstanding something about redshift itself. If there's something unexpected going on with how redshift works in extreme conditions, like very early in the universe, then we could be reading the clock wrong. Right now, most scientists are not ready to throw out lambda CDM. It still matches too much of what we see, especially on the largest scales. But the cracks are showing, and Webb is pressing on those cracks with every new image. Some researchers are building new computer models that include the strange things JWST is seeing. These models try to adjust star formation rates, gas cooling speeds, and other factors to account for the early galaxies. Others are collecting more data, hoping to confirm whether these bright, distant objects are really as old and massive as they appear. One of the hardest parts is confirming distance. Galaxies in the early universe give off only the faintest traces of light. Sometimes that light can be distorted or confused with other sources. JWST has very sharp instruments, but mistakes are still possible, especially when working with data that's this far out and this faint. That's why scientists are double-checking each discovery. They use follow-up observations, compare results across different instruments, and even turn to ground-based telescopes to help confirm redshift measurements. If the galaxies hold up under scrutiny, the pressure to revise lambda CDM will grow. Not to throw it away entirely, but to bend it or add new parts to it. This kind of challenge has happened before in science. Newton's physics gave way to Einstein's relativity when new discoveries didn't match the old equations. Now it may be time for cosmology to take another leap. Some researchers have started using new terms for this moment, phrases like cosmic dawn tension or early galaxy crisis. They reflect the growing unease among scientists who've long trusted the standard model. And while no one is declaring it broken just yet, many are saying it no longer fits as neatly as it once did. The next few years will be critical. As Webb continues to scan deeper into the sky, it will gather more evidence. We'll see whether these strange galaxies are the rule or the exception. We'll learn whether the early universe really was a place of rapid, surprising growth, or whether we've made mistakes in how we interpret what we see. JWST's hunt for population 3 stars. The very first stars in the universe are called population 3 stars. They were the first to light up the dark, empty cosmos after the Big Bang. They were made from the most basic elements, hydrogen and helium. No carbon, no oxygen, no iron. Just the raw materials left behind after the universe first cooled down. For decades, these stars have only existed in theory. No telescope has ever found one. But scientists are sure they were real, because without them, nothing we see today would make sense. These stars began the chain of events that led to everything: galaxies, planets, even life. They lived fast and died young, exploding in violent ways that spread heavier elements into space. The problem is that population 3 stars are ghosts. They lived more than 13 billion years ago. None have survived to the present day, at least not that we know of. Their light, if it still exists, would be incredibly faint and stretched out by the expansion of the universe. But if any population 3 stars left a trace, whether in small star clusters or in the glow from early galaxies, JWST should be able to see it. Looking for these stars isn't easy. They were probably very massive, burning quickly and dying after just a few million years. Because they had no heavy elements, their light looked different than the stars we're used to. Their signatures are hard to pick out, especially in the crowded fields of early galaxies. Scientists have to search for patterns that hint at metal-free stars, unusual color profiles, certain kinds of ultraviolet light, or signs of strange early supernova explosions. One of the strategies scientists are using is to examine very distant galaxies and see if their starlight shows evidence of metal-poor populations. If a galaxy seems to be filled with stars that lack carbon, oxygen, and iron, that could mean it still contains population 3 stars, or at least formed from their leftovers. Webb spectrograph can break down the light from these galaxies into detailed fingerprints. It allows scientists to measure the elements present in the starlight, even across billions of light years. Another clue comes from something called Lyman alpha emission. This is a specific kind of ultraviolet light given off by hot hydrogen gas, which was common in the early universe. Some theorists believe that clusters of population 3 stars would produce strong Lyman alpha signals due to their extreme temperatures. If JWST finds patches of space glowing with this kind of light, and those patches don't contain any evidence of heavier elements, that might point to first-generation stars. There's also the hope that Webb might see the explosion of one of these stars. Population 3 stars likely died in dramatic ways, through something called pair instability supernovae. These are different from typical star deaths. They don't leave behind a black hole or a neutron star. They just blow themselves apart completely, scattering their material in all directions. The light from one of these explosions, if caught at the right moment, would look very different from later star deaths. It would have a unique brightness curve, and the resulting chemical cloud would show no metals at all. A single catch like that could be a breakthrough. In 2023 and 2024, JWST began scanning deep fields in hopes of finding these signs. Some early data showed galaxies with extremely low metallicity, almost no signs of heavier elements. That got scientists excited. These galaxies might be homes to stars that formed shortly after the first generation, possibly even with a few population 3 stars still mixed in. There were also hints of unusual light curves from early supernovae, though none were yet confirmed as being from population 3 events. Researchers are also using computer models to predict what these stars should look like in Webb's instruments. They simulate different combinations of star sizes, temperatures, and distances, and then compare those models to real data. The challenge is that even if a signal looks promising, scientists have to rule out all other possibilities. Many things can mimic the appearance of a population 3 star, interstellar dust, overlapping galaxies, or other rare objects that can confuse the data. These stars were likely scattered across the early universe in small pockets. They didn't form in giant galaxies, but in tiny halos of gas that were just starting to come together. These halos may have merged or disappeared over time, burying the traces of population 3 stars deep inside larger systems. So even if Webb finds an extremely old galaxy, that doesn't guarantee it still holds any first-generation stars. The signals may be drowned out by newer generations that came later. Still, teams around the world are sorting through terabytes of data, looking for that one signal that stands out. They analyze the spectra of distant galaxies, looking for those that show almost no metals. They build catalogues of high redshift objects that might contain ancient stars. Each candidate gets cross-checked, verified, and compared to models. It's slow, detailed work, but it's what you have to do to reveal the very first stars that ever lived. Some think that population 3 stars may never be seen directly. They might have burned out too fast, or formed in places we can no longer observe. But even if we never see one face to face, their fingerprints might still be found, and even that would still be a huge discovery. The curious case of JADES GSZ 13-0. JADES GSZ 13-0 was found through a program called JADES, short for the JWST Advanced Deep Extragalactic Survey. Scientists pointed Webb at a small patch of sky, aiming to collect long exposures of the oldest galaxies they could find. They were looking for redshift values, measurements of how much the light from a galaxy has been stretched by the expansion of the universe. The higher the redshift, the farther away and older the galaxy is. JADES GSZ 13-0 had a redshift of about 13.2. That meant the light from this galaxy had been traveling for roughly 13.4 billion years. The universe itself is thought to be nearly 13.8 billion years old. In other words, this galaxy formed less than 400 million years after the Big Bang. That makes it one of the earliest objects ever seen by human eyes. JADES GSZ 13-0 appeared well organized, with a central core and a compact structure. Spectroscopy from Webb's NIR-SPEC instrument confirmed the redshift. The galaxy was real. For something that far back in time, JADES GSZ 13-0 had gathered a surprising amount of material. When Webb looked at the galaxy through different filters, the light it captured suggested a complex mixture of temperatures and star ages. Some stars appeared very hot and young, while others seemed older. That doesn't make sense unless the galaxy had been forming stars in waves. It wasn't just a one-time burst, it had multiple episodes of star formation, which would mean it had already lived through some kind of early cycle. This raised another possibility. Maybe JWST 13-0 wasn't the first galaxy of its kind. Maybe there were even earlier galaxies that came before it, galaxies we still haven't seen yet because they're too faint or too far away. If JWST 13-0 is already this developed at 13.4 billion years ago, it might be the result of even earlier processes. Instead of finding the beginning of galaxies, Webb may have found something that hints at an even earlier chapter, a missing piece we haven't uncovered yet. What came before this galaxy? What kind of conditions allowed it to form so quickly? Was there an even earlier population of galaxies or stars we simply haven't seen? To try and answer these questions, scientists have been simulating early universe conditions using supercomputers. They input different values, density, temperature, dark matter patterns, and try to recreate a universe that could produce something like JWST 13-0. In many cases, the simulations fail. The galaxy just shouldn't exist so soon unless something about the laws of early cosmic evolution is off. MOM-Z14, breaking distance records. JWST 13-0 does not, however, hold the title of the farthest galaxy ever discovered. That record was held by JWST 14-0, which formed nearly 300 million years after the Big Bang. And then, in May of 2025, researchers announced the discovery of MOM-Z14. Webb's sharp eye had caught its light, which began its journey just 280 million years after the Big Bang. MOM-Z14 surprisingly compact, spanning only about 240 light-years across, which is on par with the size expected for a dwarf galaxy, yet its mass is similar to the small Magellanic Cloud, around 10 to the power of 8 solar masses. It's a powerhouse packed into a tiny cosmic rock, bursting with star formation at a very high rate. JWST's NIRCam and NIRSpec instruments captured emission lines, especially nitrogen and carbon, that tell us early stars were already enriching the galaxy's gas supply. That's a major clue. Rather than being pristine and metal-free, MOM-Z14 shows signs of chemical maturity, more like the globular clusters we find in the Milky Way today. For a galaxy so young in cosmic terms, it's behaving more like a miniature version of familiar mature systems. Adding to the intrigue, MOM-Z14 seems to break another record, the highest redshift galaxy confirmed with spectroscopy as of mid-2025. Spectroscopy is key. It means scientists didn't just guess based on color and brightness. They measured its actual light fingerprint, making the finding far more robust than many photometric candidates from that time frame. This breakthrough came through the Mirage or Miracle, aka MOM survey on JWST, which re-examined suspected high redshift sources using NIRSpec. There were whispers that some might be flaws or imposters, objects blurred by dust nearer to Earth. But MOM-Z14 held steady under close spectroscopic scrutiny. Once it passed that test, it became clear this was no mirage. Galaxies that had held the record of oldest just a few short years ago, like GNZ11, which was about 13.2 billion years old, now look ancient by comparison. MOM-Z14 brings us right up to the edge of cosmic dawn. It confirms that bright, mature galaxies existed much earlier than our models suggested. A high ratio of nitrogen to carbon, similar to that in ancient globular clusters, indicates it isn't a first-generation system. Instead, MOM-Z14 feels like a descendant, already carrying the ashes of earlier stellar explosions. The galaxy seems to sit in a region that's already partially ionized, something models didn't expect until later. Portions of the universe should still have been in their dark age, filled with neutral hydrogen. This early light is already carving out ionized bubbles, a preview of how the first galaxies shaped cosmic structure. Lead author Rohan Naidu and his team have dubbed the find a cosmic miracle. Observations like this help map out how common such galaxies really are in the early universe. Early results suggest there are dozens of relatively bright galaxies already formed well within that turbulent first 500 million years. That's more than many predicted, prompting a serious rethinking of early timelines. The galaxy's compact size, intense starbirth activity, and chemical maturity all suggest that massive stars and stellar clusters formed very early, and did so in a highly efficient manner. Will future data show signs of dust, which would confirm multiple star generations? Will the galaxy fade quickly, hinting at violent feedback processes? Or will it continue forming stars, evolving into something much larger by today's standards? Space telescopes like Nancy Grace Roman, set to launch around 2027, may soon expand our sample size dramatically. Roman's broader view, but less deep, could find more galaxies in the same range, building a census of early cosmic populations. Meanwhile, the cosmology community is buzzing. MOMZ14 is a signal, a signpost for where theories may be missing crucial physics. Did dark matter collapse faster? Were star formation bursts more intense? Was cosmic rionization already underway by 280 million years? With each new image, these questions sharpen. MOMZ14 is looking back at 98% of cosmic history. That's an astonishing thought. This galaxy's light has stretched across time, offering us a glimpse into a period when the universe was still forging its identity. There's much we don't know, but Webb's record-setting discovery marks a turning point. MOMZ14 is both a triumph of technology and a challenge to our understanding, a reminder that the universe often moves faster and surprises harder than our textbooks allow. Julong, a mature spiral, when spirals were supposedly impossible. When astronomers pointed Webb's panoramic survey at a remote patch of sky, they uncovered a galaxy that defied every expectation. Named Julong, meaning torch dragon, this galaxy is a masterpiece of cosmic architecture, an elegant spiral, complete with a bulge and sweeping arms, featured at a time when such ordered structures were supposed to be impossible. At a redshift of about 5.2, Julong existed barely 1 billion years after the Big Bang. Typically, such early galaxies were thought to be chaotic and irregular, still in the process of assembly. Yet Webb's infrared clarity revealed otherwise. Julong's disk stretches some 62,000 light-years, comparable in size to the Milky Way, and it holds an estimated 100 billion solar masses of stars. Julong shows a clear classical bulge, a densely packed center of old red stars, and gracefully tiled spiral arms rich in younger stars and gas. In most early galaxies, heavy star-forming regions appear as uneven patches, not the grand design spirals seen here. According to resolved spectral energy distribution data, the red core marks an older quiescent region, while the disk continues forming stars, just like mature galaxies in our own neighborhood. Spirals require time to stabilize, galactic disks must settle, stars need to settle into orbits, and density waves to shape spiral arms. Theory said this would take several billion years. Yet, in under 1 billion years, Julong had already pieced itself together. Numerical results highlight faster than expected evolution. Julong's half-light radius is around 3.7 kiloparsec, or over 12,000 light-years, with spiral arms reaching 19 kiloparsec across. Despite its size and mass, which is nearly 10 to the power of 11 solar masses, its star formation rate sits around 66 solar masses per year, lower than anticipated for such a massive early galaxy. Julong challenges the slow burn model of galaxy formation. It likely formed its central bulge early, possibly via a burst of star formation or a central black hole phase, before building the spiral disk around it. Its dense core marks a vigorous inside-out growth history. This discovery forces astronomers to confront major puzzles. How did disk galaxies grow so quickly? Were spiral structures able to form in more tumultuous conditions than previously thought? Some suggest that spirals at early times may be short-lived phenomena. In the densely crowded early universe, galaxy mergers were common, and fragile spiral arms may form only to be destroyed soon after. Julong could be a rare glimpse of this brief window of stability. Does Julong host a central black hole that played a role in shaping its bulge? How did gas dynamics support organized rotation so rapidly? Will follow-up observations, especially with ALMA, reveal cold gas flows, star-forming clumps, or dust obscuring parts of the disk? If spiral arms can emerge this early, then cosmic evolution must be faster and more varied than lambda CDM models currently allow. The Hubble sequence, elliptical, bulge disk, spiral, now appears to have begun forming much earlier under conditions still being understood. Julong is a rare find, unearthed by Webb's high-resolution surveys. But it likely isn't alone. As next-generation infrared and submillimeter surveys expand, astronomers expect more early spirals to be revealed. Each one will help clarify whether Julong is unique or the indicator of a hidden population of mature early galaxies. The age problem, when distant galaxies look older than they should. The way scientists estimate the age of stars in a galaxy is by looking at their light. By examining the overall color of a galaxy and its spectrum, astronomers can figure out the general ages of the stars inside it. In many of the early galaxies Webb has spotted, the light is redder than expected, suggesting the stars inside are older. In some cases, the data hints that these galaxies are full of stars that should have taken over 1 billion years to form and age. One of the problems might be with redshift itself. The higher the redshift, the further away, and thus older, the object. But redshift is not a direct measurement of time. It's a measurement of the universe's expansion. That means if our understanding of expansion is off, even slightly, the redshift-age relationship might be incorrect. If the expansion rate isn't exactly what we thought, it's possible that some of the objects we think are extremely young might actually be older, or vice versa. Another possibility is that our models of how stars age might need adjustments. Maybe stars in the early universe age differently than stars today due to the different conditions in the young universe. More intense radiation, less metal in the gas clouds, higher pressures, and stronger magnetic fields. If stars aged more rapidly or burned through their fuel faster, they might appear older than they really are when we look at them today. But that would require a major shift in how we understand stellar evolution. There's also a third possibility, one that's much more troubling. Maybe the standard cosmological model is wrong. If galaxies that formed 300 million years after the Big Bang already look like they've aged over 1 billion years, then maybe the Big Bang wasn't the beginning of everything. Maybe there was a phase before it, or maybe the early universe evolved in a different way than we've assumed. This kind of thinking leads to controversial territory, models involving bouncing universes, or pre-Big Bang physics. One of the galaxies that's become a focal point in this discussion is a bright, compact galaxy found at a redshift of around 13. According to redshift alone, it existed just 330 million years after the Big Bang. But analysis of its starlight suggests it had already formed a mature population of stars. To get to that stage, it would have needed to begin forming stars within the first 100 million years of the universe, possibly even earlier. That's a tight deadline. According to current models, it should have taken time for gas to cool, for gravity to clump it together, for the first stars to light up, and for galaxies to start taking shape. Yet here we have one that seems to have skipped several steps. Other galaxies are showing the same pattern. Some are massive, over 10 billion solar masses, and appear to have a large number of old stars. Others show evidence of being passive, meaning they've already stopped forming new stars. This is especially strange, because in the early universe, galaxies were supposed to be in a frenzy of star formation, rapidly growing and changing. But instead, Webb is finding galaxies that are already calm, settled, and in some cases seemingly winding down. For now, scientists are cautious. They're calling for more detailed spectroscopy, more time with Webb and other instruments, and deeper surveys to see if these strange galaxies are rare exceptions or just the beginning of a bigger pattern. If more galaxies like this are found, it will become harder and harder to explain them away. Ultramassive black holes at redshift. 10. Seeds or anomalies. Black holes are usually born from the collapse of massive stars. Over time, they can grow by pulling in gas, dust, and even other black holes. In the modern universe, this is a long, slow process. But some of the black holes found at very high redshifts are already billions of times more massive than our Sun. These ultramassive black holes shouldn't exist yet. One of the leading examples is a black hole found at redshift of around 10. That puts it just over 400 million years after the Big Bang, and yet it's estimated to be over 1 billion solar masses. That means it has the mass of 1 billion suns, all packed into a single point. To get that big, a black hole needs time. It either needs to be fed constantly, pulling in material at the fastest possible rate, or it has to start out large, maybe much larger than we've ever seen black holes form in simulations. It's possible that some of these black holes began as normal-size stellar black holes and then ate their way to giant sizes in a short amount of time. This process is called accretion. If a black hole has enough gas around it, and if nothing interrupts its feeding, it can grow quickly. But even then, there's a limit. There's something called the Eddington limit, which puts a cap on how fast black holes can grow by accretion. Push past that limit, and the pressure from the falling gas creates so much radiation that it pushes other material away, slowing growth down. To grow from a stellar-sized black hole, say a few dozen solar masses, to over 1 billion in just a few 100 million years would require breaking that limit or finding ways to sidestep it entirely. Some scientists have proposed super Eddington accretion, where black holes somehow bypass this natural speed limit and consume matter faster than we thought was possible. But this is still being tested in models. Observations haven't yet proven that this type of growth actually happens, let alone in the extreme way needed to explain these giant early black holes. The second idea is more unusual. Maybe these black holes didn't start small at all. Maybe they were born big. These are known as direct collapse black holes. Instead of forming from a star, these black holes might have formed from enormous clouds of gas that collapsed all at once without first turning into stars. If that happened, the black holes that formed could have started out with masses of 100,000 to even 1 million suns. From there, it would be much easier for them to grow into the giants we're seeing. But to get a cloud to collapse directly into a black hole, it needs to stay extremely hot and avoid forming stars. Under normal conditions, clouds of gas cool down, break up, and form stars instead. For direct collapse to happen, very special conditions are needed, such as nearby radiation sources that heat the gas and prevent it from cooling. These situations might be rare, and yet we're seeing massive black holes all over the early universe. Some ask if these ultramassive black holes are not just rare exceptions, but part of a larger pattern. If more of them continue to be found, it could mean that something fundamental is off in our understanding of black hole formation. Another part of the mystery is their relationship with galaxies. In the modern universe, there's a clear link between black holes and the galaxies they live in. Big galaxies have big black holes, but in the early universe, we're finding some black holes that appear far more massive than the galaxies around them. It's almost like the black holes grew first, and the galaxies followed. This flips the usual story. For years, it was assumed that black holes and galaxies grew together, that they influenced each other over time in a slow feedback loop. But if the black holes are already enormous while the galaxies are still forming, that idea might not work. Maybe black holes had a head start. Maybe they acted like anchors, pulling matter together and helping galaxies form faster than expected. These early black holes are not hiding. They're actively pulling in material, heating up their surroundings, and blasting out radiation. These are called quasars, bright, energetic centers of galaxies lit up by black holes eating matter. Some of the quasars we're seeing with Webb are among the brightest objects in the universe, shining across billions of light years. That light allows us to spot them, but it also shows how powerful and active these early black holes were. One example is a quasar discovered at redshift, or around 10. Its light is coming from material swirling around the black hole at nearly the speed of light. That heat creates intense radiation, more than the combined light of billions of stars. Webb is finding several of these objects scattered across the early universe. If black holes were this energetic so early, they would have affected their surroundings. Their radiation could have heated up the gas around them, preventing more stars from forming. Or they could have triggered waves of star formation by shocking the gas. In either case, the early universe might have been shaped more by black holes than by stars or galaxies. Maybe black holes weren't just passengers in the story of galaxy formation. Maybe they were drivers. In some theories, the early universe might have had conditions that favored the formation of primordial black holes, objects that formed not from stars or gas, but from quantum fluctuations in the first moments after the Big Bang. These primordial black holes could have existed before galaxies, before stars, and maybe even before regular matter as we know it. If even a few of these survived, and if they were large enough, they might have served as seeds for the black holes we're seeing now. But this idea is controversial. There's no direct evidence yet for primordial black holes, and many questions remain about how they would behave, or even if they could form. Still, JWST's discoveries are pushing these ideas into the spotlight. The early universe is turning out to be more active than anyone expected. The ultramassive black holes at redshift 10 are windows into a time when the universe was young and wild, and when the rules we thought we understood may not have applied. Dark matter's missing signature in JWST observations. Dark matter is thought to form giant halos around galaxies. It holds them together with gravity. Without dark matter, galaxies would spin apart because their visible matter isn't enough to keep them stable. We've never directly detected a dark matter particle, but we've always been able to spot its gravitational fingerprint until now. In several of JWST's early observations, the shapes and motions of ancient galaxies don't show the strong gravitational pull we expect from dark matter. Some of these galaxies look too small, too organized, or simply too light to need dark matter at all. Others don't bend light the way they should if invisible matter were surrounding them. This doesn't just create small problems for our current models. It opens a door to something much bigger. One of the key pieces of evidence for dark matter has always come from galaxy rotation curves. In simple terms, stars orbit the centers of galaxies. If you only count the stars and gas, the outer stars should move slower than the inner ones, just like planets orbiting our sun. But when we measure how stars really move, they don't slow down. Instead, they keep spinning at high speeds, far from the center. This means something must be adding extra gravity to hold them in place. That something is believed to be a vast halo of dark matter. But in some of the galaxies Webb has observed, especially the ones in the early universe, this expected signature is weaker or even missing. The stars still spin, but not in a way that needs a heavy halo of invisible mass. In fact, some galaxies appear to have almost no dark matter at all. That's strange, because in our standard model, dark matter should have been even more important back then. The early universe was denser, more chaotic, and full of fast-moving material. Dark matter should have provided the extra gravity to help galaxies come together and stay intact. In one set of JWST images, scientists found small, compact galaxies that were incredibly bright and already well-formed just a few 100 million years after the Big Bang. But these galaxies looked too tidy, too isolated. They weren't distorted, stretched, or warped the way they should be if dark matter had been shaping their growth. Were our ideas about dark matter itself wrong? Some of the gravitational lensing events seen by JWST don't match the expected patterns. In some cases, the light bends less than expected. In others, the bending appears too smooth, without the jagged, uneven patterns that clumps of dark matter should cause. In many of the early galaxies JWST has observed, the stars and gas appear more organized. Their disks are thin and settled, with little of the wobble or warping expected in a universe still under construction. That sort of calm behavior would usually require the stabilizing effect of a dark matter halo. But if these galaxies lack halos, or if their halos are weaker than predicted, How did they manage to form so smoothly? For years, the standard idea has been that dark matter is made of particles, heavy, cold, and slow-moving ones. Some are now considering alternate types of dark matter. Warm dark matter, for example, would move faster and spread out more evenly in the early universe. That could explain why some galaxies seem to lack dense dark matter cores. Others are exploring ideas like fuzzy dark matter, where dark matter behaves more like a wave than a particle, spreading out softly and evenly rather than clumping. These models are still being tested, and JWST could help sort them out by showing us how structure really formed in the early cosmos. But there's also a more radical idea. Maybe dark matter doesn't exist at all. There have always been a few scientists who questioned the need for dark matter in the first place. Instead of adding invisible stuff to the universe, they suggest changing the rules of gravity. The idea is that at very large scales, or in very weak fields, gravity might behave differently than Newton or Einstein predicted. These theories are called modified gravity models. One of the most well-known is MOND, short for Modified Newtonian Dynamics. In MONDy and similar ideas, galaxies stay together not because of dark matter, but because gravity acts more strongly than expected at low accelerations. In the past, this idea didn't get much attention, partly because it didn't match everything we saw in galaxy clusters or lensing. But now, with JWST uncovering galaxies that seem to behave without dark matter, these old models are getting a second look. Still, there are risks in jumping to conclusions. Some of the strange results might come from the limits of our observations. We're trying to measure motion, shape, and mass using tiny bits of light. Maybe dark matter doesn't always clump with normal matter, maybe it spread differently in the early universe, or maybe it has properties that change over time. If so, we'll need to rethink the entire timeline of galaxy formation and evolution. Either way, the lack of strong dark matter signals in some of Webb's data is forcing astronomers to revisit old questions. The models we build are just maps, and sometimes, when the data comes in, those maps don't match the landscape. Hot Jupiters, cold super-Earths, the exotic zoo of JWST's exoplanets. In the search for other worlds, astronomers once thought they had a good idea of what to expect. Planets would be like those in our solar system. Small rocky ones close to the star, big gas giants farther out. But then came the first discoveries of exoplanets, and that neat, simple picture began to fall apart. Telescopes started finding worlds that didn't match anything in our solar system, giant planets whirling around their stars in just a few days. Rocky worlds larger than Earth, frozen on the edges of their systems. Strange planets with no clear place in the old theories. Now, with the JWST joining the hunt, the list of strange planets is growing faster than ever. While JWST does study the ancient universe, it also spends time on nearby stars, searching for signs of planets. Its powerful instruments can look into the atmospheres of some of these worlds and measure how they interact with their stars. It doesn't just spot planets, it can see what they're made of. And already, it's showing that the variety of planets out there is far more bizarre than anyone expected. One of the biggest surprises is how many hot Jupiters there are. These are giant gas planets, similar in size to Jupiter or Saturn, but located extremely close to their stars. They orbit in just a few days, sometimes less than 24 hours. That means they're being blasted by intense radiation. Their atmospheres heat up to thousands of degrees. Some even glow in infrared. These planets are so hot that metals like iron and titanium may be found as vapor in the air. The winds on them can reach speeds of thousands of kilometers per hour, and clouds, if they form, could be made of minerals, not water. One of the first hot Jupiters studied in detail by JWST was WASP 121b. This planet has a temperature of over 2000 degrees Celsius on its day side. That's hot enough to melt many metals. Webb looked at how the planet passed in front of its star, and then again when it passed behind. By doing this, scientists could subtract the starlight and isolate the heat from the planet itself. The telescope picked up signs of water vapor high in the atmosphere, but no sign of it forming clouds. Instead, It's likely being broken apart by the heat. There were also signs of heavy metals, possibly floating in the upper layers like invisible smoke. Then there's WSP-39b. This planet is about the same mass as Saturn, but much puffier. Its atmosphere is expanded by heat. JWST found a rich mix of chemicals in its skies, including carbon dioxide, water, and hints of sulfur-based molecules. This is the first time these molecules have been seen clearly on another world. The mix of gases doesn't match what standard models of planet formation predicted. Some of the gases should only be there if the planet formed far from the star and later migrated inward. Moving a huge planet across a solar system is no easy task. But if it didn't move, then we don't know how it ended up so close to its star with such a strange mix of chemicals. On the other side of the scale are the cold super-Earths. These are rocky or icy planets larger than Earth but smaller than Neptune. Our solar system has nothing like them. Earth is about as big as rocky planets get here, and Neptune is much bigger and made of gas and ice. But out there, super-Earths are common. Some are 2 or 3 times Earth's size, with thick atmospheres. Others are more like mega-sized versions of Mars or Mercury, cold and barren. One super-Earth, LHS 475b, orbits a small red dwarf star just 41 light-years away. When JWST looked at it, it saw a rocky world nearly the size of Earth. But something was missing, an atmosphere. If it has one, it's very thin. That's surprising, because many super-Earths are expected to have thick blankets of gas. The planet orbits very close to its star, so it could be that radiation has stripped away its air. Or maybe it never had much to begin with. Either way, it shows that not all rocky planets are Earth-like. Another cold super-Earth, Tawai 1231b, is farther from its star and much cooler. Its surface temperature might be around the freezing point of water. That puts it in a range where clouds of water or even ammonia might form. JWST hasn't fully studied this world yet, but if it does, scientists hope to detect signs of weather, clouds, and maybe even seasonal changes. A cold planet with a thick atmosphere could be a good place to search for more Earth-like conditions. Some planets seem to float between categories. There are mini-Neptunes, planets bigger than Earth, but with thick envelopes of hydrogen and helium. They aren't full gas giants, but they're not rocky either. Then there are lava worlds, where the surface is so hot that rock turns to liquid and oceans of magma cover the planet. These may have thick clouds of vaporized stone. Some planets orbit 2 stars. Some have highly tilted orbits or spin backwards. Others are so far from their stars that they're barely heated at all. In fact, some planets don't orbit any star at all. These are the so-called rogue planets, drifting alone in the dark. JWST hasn't spotted many of them yet, but its deep infrared vision makes it a good tool for finding these loners in space. Many of these worlds don't fit the classic models of planet formation. The main theory says that planets form in a disk of gas and dust around a new star. Rocky planets grow closer in, where it's warmer. Gas giants form farther out, where there's more material to build large cores and pull in gas. But hot Jupiters shouldn't exist in that model. They're too close. Super-Earths were never expected at all, and yet they're everywhere. To explain this, scientists now think that many planets move after they form. They migrate inward or outward, pulled by gravity, pushed by gas, or bounced by other planets. Some may have started far out and spiraled inward, changing their orbits over millions of years. Others may have formed from collisions and mergers. The result is a zoo of planets that are nothing like our solar system. Over the next few years, JWST will look at hundreds of worlds. Some will be hot, some cold, some with atmospheres, and some bare. In each case, the telescope will be collecting spectra that tell us what gases are present, how hot the planet is, and what the clouds are made of. If we're extremely lucky, we might even detect signs of biological activity, though that's still a long shot. Exoplanets are more varied, complex, and surprising than anyone imagined. There are no normal planets anymore. Each one is a case study in extremes. Blistering winds, freezing nights, strange skies, and alien chemistry. With each new discovery, JWST is helping to rewrite what we thought we knew about worlds beyond our own. It turns out that our solar system might be the odd one out. Out there, anything goes. TRAPPIST-1. Under infrared scrutiny, is habitability still on the table? The TRAPPIST-1 system, located just 40 light-years from Earth, has long been a focal point in the search for potentially habitable planets beyond our solar system. Discovered in 2017, the system is home to 7 Earth-sized planets, 3 of which are situated in the so-called habitable zone, the region around a star where conditions might be right for liquid water to exist on a planet's surface. For many astronomers, this discovery was a huge milestone. It was one of the first times a system with so many Earth-sized planets had been found, and the possibility that some of them might harbor life sparked an explosion of interest. Could there be liquid water on their surfaces? Could they have atmospheres thick enough to support life as we know it? The TRAPPIST-1 system, with its variety of planets, offered a perfect laboratory for studying planetary formation and habitability. But to answer these questions, scientists needed more than just the initial discoveries. They needed to study the atmospheres of these worlds in greater detail. Thanks to its advanced capabilities, Webb is able to peer deeper into the TRAPPIST-1 system and examine the planets in ways that were not possible before. JWST's observations of TRAPPIST-1 started soon after the telescope's instruments were fully calibrated and ready for science. The system, being relatively close to Earth in astronomical terms, provides an excellent target for the telescope's infrared sensors. JWST's infrared data has provided valuable insights, but it has also raised questions. Scientists had hoped that some of the planets in the TRAPPIST-1 system might have thick atmospheres capable of holding on to heat, creating stable, warm environments that could support life. However, early observations have shown that the atmospheres of some of these planets may be far thinner than previously expected. On the planets closest to the star, especially those on the inner edge of the habitable zone, the intense radiation from the star could be stripping away any atmosphere the planets might have had. If that's the case, these planets may be more akin to Venus or Mars than Earth, with no protective layer to keep the surface warm or protect it from the harshness of space. At the same time, some of the outer planets in the TRAPPIST-1 system show hints of being more promising. These planets, which are farther from the star, receive less radiation and may retain their atmospheres for longer periods of time. One of the biggest questions astronomers have been grappling with is whether these outer planets might have the right conditions for liquid water. Water is considered a key ingredient for life, and its presence would be one of the most exciting discoveries in the search for extraterrestrial life. Webb's observations have shown that some of these planets might indeed have atmospheres with the potential to support water, but it's still not clear whether liquid water could exist on their surfaces. Some of the planets appear to have atmospheres rich in certain gases, like methane and carbon dioxide. These gases are often associated with biological activity on Earth, so their presence raises the possibility that some of the planets could host life, or at least some of the chemical processes needed to support life. However, it's important to note that these gases can also be produced by geological or chemical processes unrelated to life. In other words, the presence of these gases doesn't necessarily mean that life is present, but it does suggest that there's something interesting happening on these planets that warrants further study. The most significant challenge scientists face when studying planets in the TRAPPIST-1 system is the star itself. TRAPPIST-1 is a red dwarf star, which is much smaller and cooler than our Sun. Red dwarfs are known to be prone to intense flares and radiation bursts, which could have a profound effect on the atmospheres of the planets orbiting them. These bursts of radiation could strip away the atmospheres of planets, especially those that are closer to the star, or they could cause dramatic shifts in the climates of the planets, making them inhospitable for life. What's more, the system is very different from our own. The planets are all much closer to each other than the planets in our solar system. In fact, some of the inner planets are only a few million kilometers apart. This means that the planets could be subject to significant gravitational interactions, which could affect their orbits and climates. These interactions might also cause tidal heating, a process that could generate internal heat within the planets, potentially making them more suitable for life. However, this heating could also cause instability in the planet's atmospheres, further complicating the picture. The data coming back from the telescope is rich and detailed, but it will take time to fully interpret it. While the presence of certain gases in the atmospheres of these planets is promising, it's too early to say whether any of them are truly habitable. The conditions in the TRAPPIST-1 system are extreme, and the planet's atmospheres may not be stable enough to support life as we know it. But that doesn't mean the search for life is over. The discovery of water and other key ingredients for life is still a major step forward in the ongoing exploration of exoplanets. And TRAPPIST-1 remains one of the most exciting systems to watch in the coming years. Methane, CO2, and hints of alien chemistry in exoplanet atmospheres. Methane is a potent greenhouse gas here on Earth, and on our planet, it's often produced by biological processes, particularly by microbes that thrive in environments without oxygen, such as swamps, marshes, and the guts of animals. On Earth, large amounts of methane are also released by human activities like farming and fossil fuel extraction. Because of this association with life, methane is often seen as a potential biosignature, a molecule that could indicate the presence of life. However, methane can also be produced by non-biological processes. For example, it can form through geological activity, such as volcanic eruptions, or from the interaction of water with certain types of minerals. This means that finding methane alone doesn't necessarily point to life. In the case of exoplanets, detecting methane can be even more complicated. Some planets have atmospheres rich in methane, yet there's no evidence of life on them. For instance, some of the giant gas planets in our own solar system, like Jupiter and Saturn, contain methane in their atmospheres. However, we don't think life exists on these planets. This raises the question of how to distinguish between methane produced by biological processes and methane created by other non-biological means. Carbon dioxide, or CO2, is another gas that has attracted a lot of attention. On Earth, carbon dioxide is produced by all forms of life that respire, as well as by natural processes such as volcanic eruptions and the breakdown of organic matter. Because carbon dioxide is so closely linked with both life and geological activity, its presence in an exoplanet's atmosphere isn't as definitive as one might hope. Like methane, CO2 can be produced by a variety of processes, including the weathering of rocks and the release of gases from the planet's interior. Still, its detection alongside methane could be more suggestive of life, because these two gases are often found together in Earth's atmosphere, particularly as a result of biological activity. The presence of water vapor, oxygen, and ozone can also be indicators of biological activity, though their detection is much more challenging. Oxygen, in particular, is a strong biosignature because it's primarily produced on Earth by photosynthetic organisms like plants and algae. However, oxygen can also be produced through the breakdown of water vapor by ultraviolet light from the star. Many of these gases can be produced by chemical or geological processes. Volcanic activity can produce large amounts of carbon dioxide, and methane can form through chemical reactions in the planet's interior. In addition, the conditions on the planet can play a huge role in determining what gases are present. For example, a planet with a thick, hot atmosphere might have different chemical signatures than a cooler, less dense world. So, while the detection of these gases is incredibly exciting, it doesn't automatically mean that we've found evidence of life. That said, the combination of several gases in the right proportions could suggest biological activity. For example, if methane and oxygen were found together in significant amounts on an exoplanet, that would be a much stronger indication of life. Younger planets, particularly those that are still undergoing the process of planetary formation, may have different chemical compositions than older, more stable worlds. In addition, the type of star the planet orbits plays a crucial role in determining the planet's atmospheric chemistry. Planets orbiting stars that emit a lot of ultraviolet light, for example, might have different chemical signatures than planets around cooler, more stable stars. The work of interpreting these gas signatures is still in its infancy, and the data being gathered by JWST and other telescopes will need to be studied in great detail to understand what it's really telling us. While the detection of gases like methane and carbon dioxide is incredibly exciting, it's important to remember that these gases are only part of the story. Scientists are working hard to understand how different planetary environments and processes can produce these gases, and what that might mean for the possibility of life elsewhere in the universe. Even if we find the right gases, interpreting them correctly requires a deep understanding of planetary atmospheres and the processes that govern them. A single detection isn't enough to conclude that life is present. But the data we're getting from JWST is a crucial step in building a more complete picture of exoplanetary atmospheres, and it could bring us closer to answering one of the most profound questions humanity has ever asked. Are we alone in the universe? As our technology improves and our understanding deepens, we may one day be able to confidently detect the signatures of life, or at least the conditions necessary for life, on planets far beyond our solar system. The absence of biosignatures. Is JWST looking in the wrong places? With its unprecedented ability to peer deep into the universe, JWST has detected remarkable features in distant exoplanets and their atmospheres. Yet, it has not yet found any definitive biosignatures, those chemical or physical clues that unmistakably point to biological processes. This lack of clear evidence has led some scientists to ask whether we are simply looking in the wrong places, or whether the search for life is far more challenging than we initially anticipated. One reason could be that the planets we are observing simply aren't the right candidates. While JWST is capable of analyzing a variety of exoplanets, most of the planets it has studied so far are either too large, too hot, or too distant to be ideal for life as we know it. Many of the planets JWST has observed are gas giants, like Jupiter or Neptune, whose atmospheres are not likely to harbor life. These planets are composed mostly of hydrogen and helium, with no solid surface to support life forms. Even if life were to exist on these gas giants, it would likely be very different from what we're familiar with on Earth. Even within the habitable zone, the conditions on these planets might not be suitable for life. For example, some planets might have overly thick atmospheres that trap too much heat, making them uninhabitable, while others may be too cold for liquid water to exist. The presence of water is a key ingredient, but it is not the only requirement. Other factors, such as the planet's chemical makeup, its star's radiation output, and its history, could also play a significant role in determining whether life could arise. Scientists tend to focus on detecting Earth-like biosignatures that are produced by life forms similar to those on our planet. But life on other worlds may be very different from life on Earth. We assume that life requires oxygen or methane, but extraterrestrial life could thrive on entirely different chemical processes, or in environments that we would consider inhospitable. For example, some scientists have speculated that life could exist on planets with atmospheres made primarily of ammonia or methane, or even on moons of gas giants with subsurface oceans. These environments might not produce the chemical signatures we associate with life on Earth, and so we might be overlooking them. In addition, it's important to recognize that life might exist in forms that are completely alien to us. The search for extraterrestrial life has, for the most part, been guided by the assumption that life elsewhere would share certain fundamental characteristics with life on Earth. However, there are many ways that life could potentially exist that we are not yet able to detect. For example, life forms could be based on biochemistry that we haven't considered, such as silicon-based life rather than carbon-based life. Alternatively, life could exist in extreme environments, such as on planets with extremely high radiation levels, extreme temperatures, or toxic atmospheres that are far more hostile than Earth's surface. These types of life would not produce the same biosignatures that we are searching for. Moreover, the methods we use to detect biosignatures may not be sensitive enough to pick up subtle signs of life. While JWST is incredibly powerful, it is still limited by the sensitivity of its instruments and the amount of data it can process. Detecting methane or oxygen in the atmosphere of a distant planet requires precise measurements of the planet's light. The instruments on JWST are capable of making these measurements, but the signals they receive can be faint and hard to distinguish from other sources of interference. JWST may be able to observe the light from a planet located several hundred light-years away, but the faintness of that light can make it difficult to pick out the specific chemical signatures of interest. Even the most advanced telescopes, including JWST, are limited by the sheer vastness of space. The further away a planet is, the more data it takes to discern its atmospheric makeup, and sometimes that data simply isn't there. The issue of time is another factor in the search for biosignatures. The planets that JWST is currently observing may have conditions that are only briefly suitable for life. This is particularly true for planets in the early stages of their development, which may undergo rapid changes as they evolve. For example, a planet might start with conditions that could support life, but over millions of years, it could experience catastrophic events such as volcanic eruptions, asteroid impacts, or stellar flares that could wipe out any potential life. In this case, even if life were present at some point in the past, it might no longer exist today, and any biosignatures left behind could have dissipated or been obscured. Moons of gas giants, such as Europa or Enceladus in our own solar system, have subsurface oceans beneath their icy crusts where life could potentially thrive. These types of environments might not produce the same biosignatures, and so we might be missing potential hotspots for life by focusing on the wrong kinds of planets. The absence of clear signs of life in the data from JWST doesn't mean that life doesn't exist elsewhere. It may simply mean that we need to adjust our approach. The next steps in the search for extraterrestrial life may involve looking at different types of planets, rethinking the nature of life itself, and improving our detection techniques. ALMA, Hubble, and JWST, a three-eyed view of the early universe. JWST's view of the universe is still limited to a specific wavelength range, and it can only observe certain objects or phenomena. This is where other telescopes, such as the Hubble Space Telescope, come into play. Hubble has been observing the universe in visible and ultraviolet light for decades, and it has captured some of the most iconic images of space. Although Hubble is no longer capable of observing in the same detail as JWST, it still provides valuable information about the universe's past. In particular, Hubble has helped to identify some of the earliest galaxies, which can then be studied in greater detail by JWST's infrared capabilities. Hubble's observations are crucial because they provide a bridge between the infrared observations of JWST and the radio observations made by the Atacama Large Millimeter Submillimeter Array, or ALMA. While JWST and Hubble focus on light in the optical and infrared ranges, ALMA specializes in radio wavelengths, specifically millimeter and submillimeter waves. These longer wavelengths allow ALMA to observe phenomena that are not visible in other parts of the spectrum. For example, ALMA is ideal for studying the coldest, densest regions of the universe, such as molecular clouds, where new stars and planetary systems are forming. It is also capable of detecting the faint glow of the earliest galaxies, providing a glimpse into their formation and evolution. When ALMA, Hubble, and JWST work together, they offer complementary views of the same object or event. Combining data from all three observatories gives scientists a fuller, more nuanced picture of the early universe, helping them to fill in the gaps left by any one instrument on its own. By cross-referencing the data from these different telescopes, astronomers can confirm their findings and make more accurate measurements, leading to a better understanding of how the universe has evolved over time. If JWST detects a distant galaxy in the infrared, astronomers can use Hubble's visible light data to learn more about the galaxy's structure and age. Hubble can reveal details about the galaxy's shape, its star formation activity, and its overall size. This information is crucial for understanding the galaxy's history and its place in the larger cosmic timeline. At the same time, ALMA can observe the same galaxy in radio wavelengths, looking for signs of cold gas and dust that are often present in the early universe. ALMA's observations can reveal where new stars are forming, where supernova explosions have occurred, and where black holes are growing. By combining these data, astronomers can get a more comprehensive view of the galaxy's evolution, from its earliest stages to its present-day form. Just as our eyes can only see a narrow band of visible light, each telescope can only observe a specific part of the electromagnetic spectrum. By bringing together the different wavelengths, scientists can gain a more complete understanding of the universe. This is especially important when studying the earliest galaxies, which are often faint, distant, and difficult to observe with a single telescope. By observing these galaxies in multiple wavelengths, scientists can get a more accurate picture. ALMA's high-resolution images can detect the faint emission from molecular gas and dust, revealing regions of space where new stars are being born. JWST's infrared observations, on the other hand, can measure the light from these newly formed stars and determine their age, mass, and composition. By comparing the data from both telescopes, scientists can gain a better understanding of how stars and planets formed in the early universe and how those processes have evolved over time. This is crucial for understanding the formation of our own solar system, as well as the potential for life elsewhere in the universe. The collaboration between these observatories is an example of how cutting-edge technology, when used together, can push the boundaries of scientific discovery and open new windows onto the universe. What the Nancy Grace Roman Space Telescope will do that JWST can't. While JWST will continue to provide unparalleled observations of the distant cosmos, Nancy Grace Roman Space Telescope is designed to complement its capabilities by giving astronomers a broader, more comprehensive view of the universe. One of the Roman telescope's key advantages is its ability to conduct wide-field surveys. Unlike JWST, which is a highly focused point-and-shoot telescope, Roman will be able to cover a much larger area of the sky in a single observation. This broad view is invaluable when it comes to cataloguing objects across vast regions of space. While JWST's high resolution allows it to zoom in on the intricate details of specific objects, Roman will survey large swaths of the sky, capturing everything from distant galaxies to nearby stars. This ability to survey a vast expanse in just one shot makes Roman an ideal tool for discovering rare cosmic phenomena that might be missed by other telescopes. By covering more of the sky, Roman can find more targets to study with telescopes like JWST, filling in the gaps and helping scientists make connections between objects and phenomena that might otherwise go unnoticed. One of the most exciting aspects of Roman's design is its wide-field infrared camera. This camera will enable the telescope to observe the universe in a range of wavelengths that are also of interest to JWST, but at much larger scales. This will allow Roman to discover a broad range of objects, from faint galaxies to distant supernova, and even the elusive dark energy. The collaboration between the two telescopes will create a powerful synergy, allowing them to explore the universe in ways that would be impossible with just one observatory alone. Roman's wide-field surveys will be particularly valuable for studying large-scale structures in the universe, such as galaxy clusters, dark matter, and dark energy. By measuring the way light from distant galaxies is bent by gravity, astronomers can map the distribution of dark matter throughout the universe. This is important because dark matter is thought to make up around 85% of the mass of the universe. By mapping it in this way, Roman will help to shed light on one of the biggest mysteries in cosmology. By studying how galaxies are distributed across the universe and how they are affected by dark energy, Roman will help scientists refine their understanding of this elusive phenomenon. Roman's high-resolution observations will allow astronomers to study the faintest galaxies and see how they move and interact under the influence of dark energy. This will provide crucial insights into the nature of dark energy and how it has shaped the evolution of the universe. Roman's ability to conduct large-area surveys also makes it an excellent tool for studying the life cycles of galaxies. Galaxies are constantly changing, with stars forming, dying, and being recycled in a never-ending cycle. Roman will be able to observe large populations of galaxies at different stages in their life cycle, providing valuable data on how galaxies evolve over time. While JWST's focus is on the early universe, Roman's broad surveys will allow scientists to study galaxies at a wide range of ages, from the most ancient galaxies to those that are still in the process of formation. By examining how galaxies evolve, scientists can gain insights into the processes that drive their growth and development, as well as the factors that influence their shape, size, and composition. Roman will also be able to observe the population of exoplanets in our galaxy, while JWST will be able to examine the atmospheres of individual exoplanets in detail. Roman's wide-field surveys will allow it to identify and catalogue thousands of exoplanets in a much shorter time frame. Roman's observations will provide a catalogue of exoplanets across a wide range of distances and environments, allowing scientists to identify the most promising candidates for further study. By identifying a large number of exoplanets, Roman will help to narrow down the list of targets for JWST's more detailed investigations, ensuring that the telescope's resources are used efficiently. The combination of JWST's precise, focused observations with Roman's broad, sweeping surveys promises to provide an unprecedented understanding of the universe. While JWST will continue to be the go-to instrument for studying the early universe, the Roman telescope's wide-field surveys will ensure that we have a broader, more comprehensive view of the cosmos. Together, they will allow scientists to answer some of the most fundamental questions in astrophysics, providing a deeper understanding of the cosmos and our place within it. Ground-based giants versus JWST, how the ELT, TMT, and GMT stack up. As JWST continues to redefine our understanding of the universe, a new generation of ground-based observatories is on the horizon, poised to take advantage of Earth's unique advantages in observing the sky. These include the Extremely Large Telescope, or ELT, in Chile, the 30-meter telescope, or TMT, in Hawaii, and the Giant Magellan Telescope, or GMT, in Chile, and they are set to challenge JWST's dominance in certain areas, particularly in their ability to capture high-resolution images and conduct spectroscopy with unprecedented detail. These observatories, with their immense mirrors and advanced instruments, are designed to push the boundaries of what is possible in modern astronomy. JWST's position at L2 gives it an advantage when it comes to observing infrared wavelengths. Still, ground-based telescopes, with their larger apertures and the possibility of ongoing upgrades, have a distinct edge in certain aspects, particularly in high-resolution imaging, and the ability to perform detailed spectroscopy across a wide range of wavelengths. The ELT, TMT, and GMT are each designed to feature mirrors that are many times larger than those found on current ground-based telescopes. These enormous mirrors allow them to collect much more light, giving them a significant resolution advantage over existing telescopes. The ELT, for instance, will feature a 39-meter primary mirror, while the TMT will have a 30-meter mirror, and the GMT will sport a collection of 7 8.4-meter mirrors that work together as one. This allows these telescopes to achieve resolution that rivals or even surpasses that of JWST in certain respects. While JWST's mirror measures 6.5 meters, these ground-based giants can focus on much finer details, enabling astronomers to study objects like exoplanets and distant galaxies with exquisite clarity. Both JWST and the ground-based telescopes are equipped to conduct spectroscopy, but the ground-based observatories have the upper hand when it comes to versatility. While JWST is limited in its choice of observing targets, especially given its remote location and fixed instruments, they will have the ability to perform real-time, on-the-fly changes to their observations. This is particularly important for dynamic objects like exoplanets, supernovae, or rapidly moving asteroids, where an ability to quickly adjust instruments and analyze new data is crucial. Another key advantage is their use of adaptive optics, a technology that compensates for the blurring effects of Earth's atmosphere. The Earth's atmosphere, while essential for life, also causes the light from distant objects to bend and distort, limiting the sharpness of ground-based observations. Adaptive optics systems work by using deformable mirrors and real-time feedback from specialized sensors to correct these distortions, effectively allowing ground-based telescopes to see through the atmosphere. JWST, in contrast, doesn't have to contend with this issue, as it operates in the vacuum of space. However, the addition of adaptive optics means that the ground-based telescopes can deliver nearly perfect images, achieving a level of detail that could be extremely challenging to match, even with the best space-based instruments. For example, they will be able to study exoplanet atmospheres in unprecedented detail using their advanced spectrographs. While JWST has already provided valuable insights into the potential habitability of exoplanets, the ground-based telescopes will offer a different approach. They will allow for more accurate measurements of atmospheric composition, surface conditions, and even potential signs of life. When it comes to studying black holes, the ground-based telescopes also have an advantage. While JWST can provide detailed infrared images of distant black holes and the material surrounding them, they will offer sharper views of the larger-scale environments in which these black holes exist. Their ability to study the motions of stars and gas in the vicinity of supermassive black holes will provide critical information about their growth, behavior, and role in galaxy evolution. However, their size does not guarantee that they will be able to see everything JWST can. There are certain observations that JWST can make that will remain outside the reach of the ground-based observatories, particularly in the infrared wavelengths. JWST's specialized instruments allow it to peer deeper into the universe. Furthermore, because the ground-based telescopes are Earth-bound, they will be limited by factors such as weather, atmospheric conditions, and the amount of time they can observe a given region of the sky. In addition to their technological advantages, they will also face challenges that JWST does not. For one, they will need to contend with the potential for light pollution, especially as their locations are close to populated areas. The increased visibility of ground-based observatories means that they must take extra precautions to mitigate the impact of artificial light on their observations. Furthermore, ground-based telescopes will also face the challenge of operating in harsh environmental conditions, such as the dust storms and volcanic activity that can sometimes impact observatories in places like Chile and Hawaii. Still, each of these telescopes brings unique strengths to the table, and together they will allow astronomers to explore the cosmos in ways that were previously unimaginable. The LUVOIR and HABEX concepts, visions for a post-JWST future. After JWST has completed its groundbreaking work in infrared astronomy, two conceptual missions, LUVOIR, or the Large Ultraviolet/Optical/Infrared Surveyor, and HABEX, or the Habitable Exoplanet Observatory, stand at the forefront of ideas for future space observatories. These ambitious concepts, though still in the planning and design phases, promise to take our understanding of exoplanets and their potential for supporting life to new heights. LUVOIR and HABEX are similar in some respects, both aiming to advance our ability to detect and study Earth-like exoplanets in unprecedented detail. But they differ in their focus, the techniques they would use, and their potential to expand on the achievements of JWST. Their designs are meant to address some of the limitations that JWST may face as we look for signs of life on distant planets. LUVOIR, a mission concept developed by NASA, is envisioned as a large space telescope with a mirror size far larger than JWST's 6.5-meter diameter. The LUVOIR concept, would feature a mirror in the range of 15 meters, enabling it to capture far more light and produce much sharper images. This would allow LUVOIR to study exoplanets with a level of detail that is currently unattainable. The large size of the mirror would enable LUVOIR to observe distant worlds in visible, ultraviolet, and infrared light, making it a versatile tool for a wide range of astrophysical investigations. Unlike JWST, which specializes in infrared observations, LUVOIR would be capable of directly imaging exoplanets in visible light, opening the door to detailed observations of their surfaces and atmospheres. LUVOIR could directly image Earth-like planets and observe their atmospheres, searching for chemical signatures that could indicate the presence of life. Its combination of a large mirror and multiple observing modes would make it an ideal tool for studying these distant worlds in detail, and its ability to capture high-resolution images of exoplanets would allow astronomers to probe their surface features, weather patterns, and even potential signs of habitability. HABEX, another concept developed by NASA, shares some similarities with LUVOIR, but with a more specific focus on the search for life beyond Earth. HABEX would be optimized for studying Earth-like exoplanets in more detail than ever before, particularly those that orbit stars similar to our Sun. One of the key elements of the HABEX concept is its ability to directly image exoplanets using a starshade, an innovative technology that would block out the light from a star, allowing the telescope to observe the dim light reflected by planets in its habitable zone. This would allow astronomers to study exoplanets in a way that JWST and other telescopes are currently unable to do, with a level of precision that could reveal the planet's atmospheres and surface conditions. HABEX would focus heavily on detecting biosignatures. Similar to LUVOIR, HABEX would observe the composition of exoplanet atmospheres, looking for gases that are typically associated with life, such as oxygen, methane, and nitrous oxide. These biosignatures could potentially indicate the presence of life, even if we don't know exactly what that life might look like. HABEX's ability to directly observe the light coming from exoplanets would allow astronomers to search for these signatures in a way that is not possible with current or planned space telescopes, making it an invaluable tool. Both LUVOIR and HABEX would be capable of studying objects much further away than JWST, with the potential to observe exoplanets around stars up to several hundred light-years away. Their ability to resolve the light from individual planets would enable them to observe and characterize distant worlds in ways that are currently impossible. This would provide valuable insights into the formation and evolution of planets, the conditions necessary for life, and the potential for life beyond our solar system. In addition to their focus on exoplanets, LUVOIR and HABEX would also provide significant contributions to the study of other astronomical objects. LUVOIR, with its large mirror and broad wavelength coverage, could be used to study the formation of galaxies, stars, and black holes. HABEX, while more focused on exoplanets, would also be capable of observing stars, nebulae, and distant galaxies, providing new insights into the life cycles of stars and the conditions that lead to the formation of planets. Both missions would also offer exciting opportunities to test and refine the technologies necessary for future space exploration. The development of starshades, coronagraphs, and other advanced instruments would push the boundaries of what is possible in space-based astronomy, laying the groundwork for even more ambitious missions in the future. LUVOIR and HABEX would also help improve our understanding of how to design and build large, complex space telescopes, providing valuable lessons for the construction of future observatories. While both LUVOIR and HABEX are still in the conceptual phase, the potential for these missions to transform our understanding of exoplanets and the search for life is immense. Whether it's through the study of atmospheric composition, surface features, or potential biosignatures, LUVOIR and HABEX would help us explore the potential for life and push the boundaries of our knowledge. Could the solar gravitational lens be the final telescope? For as long as humans have looked at the sky, we've been trying to make our eyes stronger. From glass lenses in Galileo's time to mirrors launched into space, each telescope has been a step closer to seeing more clearly and farther out. But even with the James Webb Space Telescope, with all its complexity and power, we are still only getting glimpses. We see light spread across great distances. We infer shapes and colors. But when it comes to seeing a distant exoplanet the way we see our own world, from oceans to continents, even down to clouds, we're not there yet. There is, however, a concept that might change that. It's based on a simple and well-tested effect from general relativity. The idea is this: gravity bends light. When light from a distant object passes near a massive body, like a star, the light curves around it. This bending can focus the light, acting like a lens. We've seen this happen around distant galaxies, but the most intriguing application may be much closer to home, using our own sun as the lens. The Solar Gravitational Lens, or SGL, is not a telescope in the usual sense. It doesn't involve a giant dish or a polished mirror. Instead, it uses the curved space around the sun to collect and focus light from something behind it. If we position a camera or spacecraft at just the right point on the other side of the sun, specifically around 550 astronomical units away, we could, in theory, see distant planets with detail far beyond what any current or planned telescope could provide. To understand why this is so powerful, it's helpful to think in terms of magnification. The light from a far-off planet, maybe 100 light-years away, would pass close to the sun. The sun's gravity bends that light inward, focusing it along a line extending outward into space. If a spacecraft were placed along that line, starting at around 550 AU and stretching beyond, it would be in position to gather the focused light. What you get is an enormous boost in resolution, not just a few pixels across a planet's disk, not even a fuzzy map, but potentially an image sharp enough to see surface features, mountains, forests, oceans, weather systems. The numbers are almost unbelievable. Theoretically, a telescope at the Solar Gravitational Lens focal region could achieve resolution equivalent to billions of pixels across a planet the size of Earth. That's not an exaggeration. If the system could be built and stabilized well enough, we could map the surface of an exoplanet 100 light-years away to a level of detail similar to satellite images of Earth. With that kind of detail, scientists could look for patterns that hint at vegetation. They could track weather patterns. They might even catch glimpses of artificial structures, though that's far into speculation. More realistically, they could search for signs of life that are impossible to detect with traditional telescopes. Biosignatures would become clearer. Surface chemistry could be studied remotely. It would be, in many ways, the ultimate tool for exoplanet research. Of course, all of this is easier said than done. The first problem is distance. The Voyager 1 spacecraft, which launched in 1977, is only about 160 AU from the Sun today. A spacecraft would need to travel more than 3 times farther than that. 550 AU just to reach the beginning of the focal zone, and ideally much farther to allow for better imaging. At current speeds, that would take decades. But new propulsion ideas are being explored. Solar sails, nuclear electric propulsion, even laser-pushed probes. These could reduce the time needed to something closer to 20 or 30 years, depending on the method. The second challenge is alignment. The light from the distant planet gets focused into a very narrow area. The spacecraft would need to be positioned with incredible precision to catch that light, and the planet it's imaging would move. Its star would move. The spacecraft would need to be able to track those changes while remaining stable. This isn't a task for one telescope. It might require a swarm of probes or a telescope with very fine steering and guidance systems. Another issue is background light. The sun isn't a perfect lens. It also shines very brightly in all directions. Any telescope near it would have to deal with the glare. Coronagraphs, devices that block out the sun's light, would be essential. They're already used in solar telescopes, but the demands here would be even greater. The telescope would have to block out nearly all of the sun's light while collecting the faint, bent light from the distant target. That requires a level of control and optical engineering that goes beyond anything currently flying. Then there's the data. The amount of information gathered from even one exoplanet would be enormous. A mission like this would not just take a few pictures. It would likely scan the focal area, collecting data over time and using complex processing to reconstruct the image. This is similar to how computed tomography, or CT scans, work in medicine. The image is built from many measurements taken from different angles. A solar gravitational lens mission would do something like that, rotating and moving slowly to gather a full picture of the exoplanet over time. Despite all these challenges, researchers have already started modeling what such a mission might look like. NASA and several university teams have published papers exploring the physics, mission design, and engineering requirements. The results are encouraging. Nothing in the laws of physics prevents the mission. It's just a question of technology and patience. Some call this the final telescope because it could offer the ultimate in observational power, not in terms of seeing everything at once, but in terms of what it could do with one target, one planet, one deep look. It's not about scanning the whole galaxy. It's about choosing one world and studying it with a level of detail that rivals how we view our own planet. If it works, it could change everything. For the first time, we could see another Earth, not as a dot, not as a spectrum, but as a place. A world with shape, structure, and maybe even signs of life. A world that feels real, not imagined. The kind of image that could inspire future generations, shape policies, and maybe even decide where we go next. In a way, this concept captures something deeper than just science. Not just what we can see, but what we dare to see. What kind of questions we ask, and what kind of answers we hope to find. The solar gravitational lens is not an easy path forward. It's long, it's slow. It demands more precision than anything we've done before. But the reward is something we've always dreamed of, a clear window into another world. What would it take to build a telescope on the far side of the Moon? There's a place in the solar system that's both close and distant at the same time. It's only about 384,000 kilometers away, roughly a 3-day trip with current rockets. We see it all the time in the sky, glowing white or golden depending on the night. But half of it is always turned away from us. The far side of the Moon, a place hidden from Earth, silent, untouched by human noise, and almost completely free of interference from our planet. That silence might be the most valuable thing about it. The far side of the Moon could be the perfect location for a telescope, especially a radio telescope. On Earth, we're surrounded by a constant buzz of radio waves, cell phones, satellites, radar systems, television signals, even microwave ovens. All of it creates background noise that makes deep space radio observations harder. Even space-based telescopes like Hubble and JWST can't fully escape it, because they're still within reach of some of Earth's interference. But on the far side of the Moon, there's a natural radio shadow. The Moon itself blocks Earth's signals. What you get is a quiet zone, a deep calm in the chaos, perfect for listening to the faintest whispers from the universe. Building a telescope there would open up a new window. Radio signals from the early universe, dating back to just a few 100 million years after the Big Bang, have been stretched out by the expansion of the universe. These long, low-frequency signals are nearly impossible to detect from Earth, both because of interference and because our own atmosphere blocks them. A radio telescope on the far side of the Moon could listen to those ancient signals directly. It could probe the cosmic dark ages, a time before the first stars lit up. Of course, getting a telescope there is no small task. Right now, most of our lunar missions are small robotic landers or orbiters, but a large telescope needs support structures, power systems, possibly crews to assemble it, or at the very least, advanced robotics. One idea scientists have explored is using the natural shape of lunar craters. Some craters on the far side of the Moon are enormous, with smooth, bowl-shaped interiors. If a giant radio dish were to be built inside one of these craters, the walls would naturally help collect and focus radio waves. It's similar to how the Arecibo Observatory in Puerto Rico worked before it collapsed, using the land itself as part of the telescope. But unlike Arecibo, the Moon has no wind, no rain, no vegetation. Structures built there could last for thousands, even millions of years if properly maintained. Another approach would be to deploy many small antennas across a wide area, essentially creating a radio array. These could be wire loops or simple poles spread out across the lunar surface. When linked together through a central computer system, they could simulate a much larger telescope using a technique called interferometry. This is the same method used by Earth-based telescopes like the Very Large Array in New Mexico, or the Event Horizon telescope that imaged the shadow of a black hole. But on the Moon, these arrays could be far larger, more sensitive, and totally shielded from Earth's radio pollution. Setting all of this up would take coordination between nations or space agencies. It would take engineers designing tools that can handle the extreme heat swings on the Moon, burning hot during the day, freezing cold at night. It would take robots capable of navigating the dusty, powdery terrain. Lunar dust is not like Earth dust. It's sharp, sticky, and gets into everything. It's been one of the major concerns in every Moon mission since Apollo. This would be a mission 10 times more ambitious than JWST. Then there's the matter of communication. The far side of the Moon never faces Earth. You can't beam data directly back like you would from an Earth-facing satellite. A telescope there would need a relay system, either a satellite placed in orbit around the Moon, or a series of communication stations set up on the surface to bounce the signals around to the near side and then back to Earth. China has already tested this approach. In 2018, they launched a satellite called Keqiao, which orbits in a special point behind the Moon, keeping constant line of sight with both Earth and their lander on the far side. It works. The concept is proven. Beyond radio telescopes, there's also growing interest in placing optical or infrared telescopes on the Moon. The Moon has several advantages over even Earth-orbiting telescopes. First, the lunar surface is incredibly stable. There's almost no seismic activity. Once something is anchored there, it stays steady. That makes it easier to do long, deep exposures of faint galaxies or distant stars. Second, the Moon has a long night, roughly 14 Earth days. That gives a telescope a long window to cool down naturally and gather light without heat getting in the way, especially important for infrared observations. Some designs even imagine putting telescopes in lunar lava tubes, underground tunnels carved by ancient volcanic activity. These tubes are shielded from radiation, protected from micrometeorite impacts, and thermally stable. They could house sensitive instruments or even act as observatories themselves, with long tunnels turned into light-collecting paths. The Moon also offers something that's often overlooked: permanence. A telescope in Earth orbit only lasts as long as its instruments can stay functional, typically a few decades. Even if nothing goes wrong, they eventually run out of fuel or power. But on the Moon, with solar panels and proper shielding, a telescope could work for centuries. It could be repaired or upgraded by future missions. It could be part of a growing scientific outpost, a first step toward a long-term human presence in deep space research. Many of the technologies needed are already being developed. NASA's Artemis program is working on returning astronauts to the Moon. Private companies like SpaceX and Blue Origin are building larger landers and cargo systems. Robotic explorers are getting smarter, more autonomous, and better at working in harsh environments. And international interest is growing. China, Europe, and India are all exploring lunar science missions. The timing may be right for collaboration. Still, it won't be cheap. Building and launching even a modest telescope would cost billions. It would need political will, long-term funding, and international agreements to make sure the far side remains a shared scientific zone. There are already concerns about space becoming a battleground for territory and resources. The Moon's far side could be seen as a neutral ground, a place where science can happen without the noise, literal and figurative, of Earth, quantum gravity, string theory, and the unexpected in high redshift data. Quantum gravity is the term scientists use for efforts to understand gravity in the context of quantum mechanics. Right now, gravity is explained by general relativity, and the other three fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, are explained by quantum field theory. But when scientists try to bring gravity into that same quantum picture, the math starts to break down. A full theory of quantum gravity doesn't yet exist, but string theory is one of the most studied ideas in this search. And surprisingly, the early universe may be the best place to test it. That's because the further back in time you go, the smaller and hotter the universe was. In those first moments after the Big Bang, energy levels were incredibly high, and space and time were compressed into conditions we can't recreate on Earth. In those moments, both quantum mechanics and gravity were in full effect. This is the exact environment where theories like string theory are supposed to work. String theory proposes that all particles are not points, but tiny vibrating strings. Each string's vibration corresponds to a different particle or force. What's important is that string theory includes gravity automatically. It predicts a particle called the graviton, which carries the gravitational force in the quantum world. String theory also needs extra dimensions beyond the three we can see, and the one we move through in time. In most versions, there are 10 or 11 dimensions in total. These extra dimensions are thought to be compacted into shapes so small we can't detect them directly. JWST is peering into an era when those extra dimensions might have played a larger role, or when quantum effects were shaping space and matter in a more noticeable way. Some researchers believe that the unexpected brightness and structure of early galaxies could suggest that gravity was behaving differently back then. In general relativity, gravity gets weaker as you move away from a mass, and it affects the shape of space and time. But what if in the early universe, gravity acted more strongly, or even repelled, rather than attracted under certain conditions? Some string theory models allow for temporary changes in the behavior of gravity. These are highly theoretical ideas, but if JWST continues to see galaxies that shouldn't be there, scientists may have to consider them more seriously. There are also ideas within quantum gravity about how space and time themselves might not be continuous. Some versions suggest that space-time is made of tiny, discrete chunks, like the pixels on a screen. These ideas, often called quantum loop gravity or related theories, suggest that the early universe could have gone through cycles. In one possibility, the universe didn't begin with a single Big Bang, but instead bounced from a previous contraction phase. That kind of scenario could make the early formation of galaxies easier to explain, because the seeds of structure would have had more time to form. Even the cosmic inflation theory, which many still accept as the best explanation for the smoothness and flatness of the universe, doesn't yet fit cleanly with quantum gravity. Inflation involves an energy field that drove the universe to expand faster than the speed of light for a tiny fraction of a second. But what started this inflation? What field caused it? And what caused it to stop? These questions don't yet have answers that fit well into quantum gravity or string theory. If we see too many massive galaxies too early, or if the shapes of those galaxies show signs of unusual behavior in the surrounding space, that could be a signal that something about inflation, or even about the nature of space itself, is different. These kinds of findings might point toward new physics, things that string theory and other models might help explain or fail to explain. String theory, for example, includes something called the landscape, which refers to a vast number of possible universes, each with different physical laws and constants. It's one way to try to explain why our universe has the conditions it does. If some of the high redshift galaxies seem to belong to a universe with slightly different rules, it might hint that our cosmic neighborhood is part of a broader multiverse. A radical idea, but one that string theory doesn't rule out. Another place where early universe observations connect to quantum gravity is in the study of primordial black holes. JWST may not be able to see these black holes directly, but it could see their effects, like gravitational lensing. If enough of these objects are found, it could change how we understand both galaxy formation and dark matter. Some string theory versions even suggest that certain black holes might be tied to the shape of extra dimensions, or that they could be portals to other regions of space-time. Right now, these are still just ideas and models. But telescopes like JWST are finally reaching the distances where these theories might be testable. For decades, string theory and quantum gravity lived in the world of pure math and thought experiments. But the data coming in from the early universe is starting to touch on the kinds of conditions where these models matter. The challenge, as always, is that we can't do experiments in the lab to confirm what happened 13 billion years ago. We can only gather as much information as possible, build models, and test how well they fit the observations. Theories like string theory can predict how gravity might behave differently under extreme conditions. But now that we're seeing those conditions with JWST, those predictions need to be sharpened. If a theory can't match the data, it needs to change or be replaced. Some scientists are hopeful that future observations will either support or rule out entire families of theories. Some string theory models suggest dark matter is made of axions or other exotic particles. If those particles leave a detectable imprint in galaxy behavior, it might offer a way to prove or disprove the theory. The simulation tension: why JWST doesn't match the universe we render. In modern astronomy, simulations are the silent scaffolding behind every grand theory. Scientists use them to build models of how galaxies form, how stars cluster, and how the early universe evolved. These simulations are vast computer programs that take in the known laws of physics and try to recreate the universe, step by step, from its first seconds to billions of years later. One of the most famous of these is called Illustris. Another is known as Eagle. These programs have guided astronomers for years, helping to explain what telescopes saw. But tension has been growing ever since JWST started releasing its first deep images. Where simulations expected just a few small galaxies, JWST found dozens. Where the simulation said those galaxies should be dim and not well formed, JWST found bright, well-shaped structures, some with spirals, others with defined bulges, and many with heavy elements already in place. Simulations like Illustris and Eagle are built on the idea that small changes in the early universe grow over time into large structures. These changes, called density fluctuations, are tiny differences in how much matter existed in different places shortly after the Big Bang. Over millions and then billions of years, gravity pulls matter toward the denser areas. Galaxies form in those places. Stars form inside the galaxies. Over time, they grow bigger and merge with others. That's the general idea. These simulations have helped explain the large-scale structure of the universe, the way galaxies seem to line up in long filaments, with voids between them. But JWST is peering much closer to the start of this whole process. It's revealing galaxies that are 10 times more massive than they should be for the time period they are in. Some show signs of heavy elements that should take generations of stars to build up. Others seem to be in stable disks, with a clear order rather than chaotic clusters. One possibility is that the simulations aren't starting with the right assumptions. When building a model of the universe, scientists must feed the program with certain starting points, what they call initial conditions. These include things like the total amount of matter, the properties of dark matter, the strength of gravity, the temperature of the universe, and how matter clumps together at small scales. Even small changes in these numbers can lead to very different outcomes billions of years later. In some cases, these inputs are based on data from the CMB, gathered by missions like Planck and WMAP. But that data shows a smooth and well-behaved early universe. JWST, however, is now pointing to a universe that builds complexity much faster than expected. If these two observations are both correct, then something must be off in how simulations link the beginning of time to what comes next. Another issue may lie in how simulations treat feedback. In astrophysics, Feedback refers to how stars, supernovae, and black holes pump energy back into their surroundings. This energy can slow down star formation, push gas out of galaxies, or even stop galaxies from growing altogether. Simulations try to include feedback by writing rules into the program, what scientists call subgrid physics. But these rules are based on simplified models because the fine details happen at scales too small for the simulation to fully track. If JWST is seeing galaxies forming more quickly and efficiently than the simulations allow, it might mean the feedback effects are too strong in the models. Maybe stars don't push out as much gas as we thought. Maybe black holes don't heat up the surroundings as much. Or maybe there's some other process we haven't included at all, something that helps galaxies hold onto their gas and form stars earlier. It's also possible that the simulations don't handle small-scale structure well. Illustris and Eagle focus on large volumes of space, hundreds of millions of light-years across. To do that, they have to limit the level of detail. They smooth out smaller clumps and ignore individual stars. That's fine for understanding the broad structure of the universe. But JWST is showing galaxies at very small scales, especially in the early universe, where tiny differences can have a big impact. A few dense pockets of gas, under just the right conditions, could have formed stars and galaxies much faster than the average. If simulations miss these pockets, they miss the galaxies too. Some researchers are now calling for a new generation of simulations, ones that are tailored to match JWST's findings. These would need to model the early universe at higher resolution and include a wider range of physics. They might need to adjust the nature of dark matter or rethink how inflation set the initial structure. They may even need to explore more radical ideas, like early black holes that help seed galaxy growth, or exotic forms of energy that help matter clump together faster. The problem isn't that the simulations are wrong. It's that they were designed to match the data we had before. That data came mostly from Hubble and from large surveys of the modern universe. JWST is showing that the early universe may have been more active and a lot more varied. This gap between simulation and observation is a clue. Every time a telescope finds something that doesn't match expectations, science has a chance to grow. Just as older theories once had to make room for relativity and quantum mechanics, today's models of galaxy formation may have to make room for whatever reality JWST is uncovering. Astronomers are combing through the data, comparing every pixel with their digital predictions. Some are tweaking existing simulations. Others are starting new ones from scratch. Across the world, computer servers are running day and night, crunching numbers, simulating stars, testing new versions of cosmic history, and images from JWST keep arriving, deep and full of unexpected details. The temporal illusion. What does it mean when ancient galaxies look mature? From the beginning, physics has told us that time is not a fixed thing. Einstein's theory of relativity showed that time stretches and bends depending on speed and gravity. A clock on a mountain ticks slightly faster than a clock at sea level. A clock on a spaceship flying near the speed of light ticks more slowly than one on Earth. In everyday life, these differences are too small to notice. But across the universe, across billions of years in extreme conditions, these effects can matter. Could it be that the early universe had places where time moved differently? Maybe some areas of the universe went through rapid evolution, while others took longer to get going. That would mean galaxies that formed early and fast might just look strange, because they developed in a region with different rules. We might be seeing only the brightest and most developed examples, simply because those are easiest to detect. The more ordinary and slower-growing galaxies might still be hiding in the shadows, waiting for deeper surveys to find them. There's also the possibility that light from these ancient galaxies carries built-in confusion. As it travels across space, light stretches due to the expansion of the universe. But what if our understanding of this process is incomplete? If something about the early universe changed the way light behaves over time, perhaps due to interactions with unknown particles or fields, then our measurements of age and distance might be slightly off. Even a small error in how we interpret redshift could mean the difference between a galaxy being 300 million years old versus 800 million years old. That's a big deal in terms of development. It could turn a mysterious, mature-looking galaxy into one that simply had more time to grow than we thought. Another idea is that our sense of how galaxies evolve is based too much on our local universe. Most of our models come from watching nearby galaxies and then trying to work backwards. But that assumes galaxy evolution has always followed the same rules. JWST is showing us galaxies that might have formed in environments we've never seen before. Under those extreme conditions, maybe star formation happens more quickly. Maybe black holes form earlier. Maybe gas collapses into stars with greater speed and less resistance. If so, then galaxies might not need billions of years to look mature. They could reach that stage in just a few 100 million. For most of modern astronomy, we've thought of the universe as a kind of smooth unfolding of time. From the Big Bang, things cool down, galaxies form slowly, stars light up, and eventually planets take shape. It's like a long film played in order, frame by frame. But maybe the early part of that film is missing some key scenes. Maybe nature found a way to fast forward parts of the story. If some galaxies look old while being young, perhaps old is the wrong word. Maybe we're confusing maturity with brightness, or size, or shape. A galaxy might appear organized not because it's had time to develop, but because it formed under conditions that allowed for order from the start. It's like seeing a fully built house and assuming it took months to construct, when in fact it was built quickly using tools or methods we didn't know existed. The timeline of the universe, once thought to be fairly settled, is now being questioned. The story unfolding now is about how we think time works on a grand scale. It's about asking whether the past can be stranger than we imagined. The deeper we look, the more that illusion of time seems to invite a second glance. JWST's role in unpacking cosmic geometry. When we talk about space, it's easy to picture shapes. We think of distances, directions, volumes, and curves. We can imagine a flat floor, a round Earth, or a spinning galaxy. But time is harder to picture. It feels like something separate, something that just moves forward, like a line drawn from left to right. We live through it, but we don't really see it. Yet at the deepest level, time and space are connected. Together, they form something called space-time, and that whole structure can bend, stretch, or even twist. JWST is giving us a clearer view of how that structure behaves. By looking farther back in time, it's allowing scientists to study not just what is out there, but how the universe itself is shaped. And in doing so, it may help us answer one of the oldest and strangest questions in science. Are we thinking about time the wrong way? At the biggest scale, space-time has a shape. That might sound strange, but it comes from Einstein's theory of general relativity. In that theory, gravity isn't a force that pulls objects together. Instead, it's the bending of space-time caused by mass and energy. A planet bends the space around it, and that bending guides the movement of other objects. The more mass, the more bending. The same goes for the entire universe. If we zoom out far enough, the universe has an overall shape, one that affects how galaxies move, how light travels, and even how time flows. For a long time, scientists debated what that shape might be. Is the universe flat, like an infinite sheet? Is it open, curving outward like a saddle? Or is it closed, like the surface of a sphere? Each shape leads to different predictions about how fast the universe expands, how it might end, and how time behaves inside it. Observations from satellites like WMAP and Planck showed that the universe seems to be very close to flat. That means, on average, light travels in straight lines over huge distances. But those satellites couldn't look as far back or with as much detail as JWST can. Now, with JWST, we're seeing things that don't quite fit the old picture, and these surprises are making some physicists wonder if our model of time and space is missing something. Maybe the early universe was more curved, and that helped galaxies form more quickly. Or maybe time itself flowed differently back then. If true, this could explain why some ancient galaxies look too mature. They weren't forming faster, they were just living through time at a different rate. In some versions of this idea, time isn't a straight arrow. It might be more like a wave or a spiral. Different parts of the universe might experience time differently, depending on where they are and how much mass surrounds them. This is already true in small ways. Time moves more slowly near a black hole than it does far away. We've tested this with atomic clocks. But what if the same kind of time distortion happens on the scale of the universe itself? JWST's sharp eye lets us measure distances and ages with much more accuracy. But sometimes, the age we calculate from the redshift doesn't match what we expect based on how the galaxy looks. That mismatch could mean our timeline is off. And if the timeline is off, our sense of how time flows may be flawed too. We don't know exactly how inflation ended, or if it ended the same way everywhere. It's possible that time began to flow at different rates in different regions. Some parts of the universe might have aged more quickly than others. If JWST sees galaxies that formed in those faster aging areas, it would explain why they appear too advanced for their age. Another idea comes from quantum physics. At the smallest scales, time might not be continuous. It could come in tiny packets, like frames in a film reel. If that's true, then the early universe, being very dense and hot, may have ticked through those frames at a different pace. The flow of time could be linked to energy levels. When the energy was higher, time moved differently. As the universe expanded and cooled, the rhythm of time changed. Galaxies that formed early might have experienced millions of years in what, to us, looks like a very short time. This leads to the concept of emergent time. In some theories, time isn't a basic ingredient of the universe. It's something that comes out of deeper rules, like temperature coming from the motion of atoms. The early universe could have been in a state where time, as we know it, hadn't fully formed yet. JWST might be seeing the tail end of that strange era. Even the direction of time is a mystery. We feel it going forward because we remember the past, not the future. But at the level of physics, most equations work the same whether time runs forward or backward. The arrow of time seems to be tied to entropy, the idea that things go from order to disorder. But in the very early universe, things were extremely ordered. That raises the question, where did the arrow of time come from? If time had a different structure back then, maybe the arrow didn't even exist yet. Maybe time didn't have a clear direction. JWST won't answer all of these questions on its own, but it gives us the data we need to start asking them in a serious way. By comparing the shapes, ages, and motions of ancient galaxies, scientists can begin to test different models of space-time. They can look for patterns that suggest time was behaving in unusual ways. They can explore whether cosmic expansion followed a smooth path or if there were twists and turns we haven't accounted for. The telescope looking into the past may end up changing how we see the present and how we imagine the future. Why JWST sees in infrared. Space is filled with clouds of dust. These clouds can hide stars, planets, and galaxies from view. Visible light can't get through them, it bounces off or gets scattered. But infrared light can pass through. It slips between particles of dust, revealing what's hidden inside. This means Webb can see stars forming inside dusty clouds. It can spot young planets still surrounded by disks of gas. And it can peer into places that have remained dark and mysterious for decades. In our own galaxy, Webb can see into stellar nurseries, places where new stars are born. These nurseries are thick with dust. In visible light, they look like dark blobs. But in infrared, they light up with activity. Webb can spot the moment a star begins to form. It can see the early shapes of planets as they gather in rings of dust. It's like watching the universe build itself from the inside out. Looking in infrared also helps when it comes to spotting planets around other stars. Planets don't shine the way stars do. They reflect light and give off heat. In visible light, the glare from a nearby star can easily hide a planet. But in infrared, the heat of the planet stands out. Webb has special instruments that can block the light from a star, letting it isolate the warm signal of the planet nearby. This allows scientists to study not just the presence of a planet, but what its atmosphere is made of. The same method works on galaxies. Distant galaxies that are too faint in visible light show up clearly in infrared. Some of these galaxies are so ancient that they were formed just 300 or 400 million years after the Big Bang. That might sound like a long time, but in cosmic terms, it's very early. The light from those galaxies has been traveling for over 13 billion years. That light is now stretched so far into the infrared that only a telescope as sensitive as Webb can catch it. To pick up these faint signals, JWST had to be kept extremely cold. Any heat from the telescope itself could hide or distort the infrared signals from space. That's why the sun shield was so important. On one side of the shield, facing the sun, it gets as hot as 110 degrees Celsius or 230 degrees Fahrenheit. But on the other side, where the telescope sits, it drops to around minus 223 degrees Celsius or minus 370 degrees Fahrenheit. That cold allows Webb to detect heat from faraway stars and galaxies without getting blinded by its own temperature. Infrared also lets us see how galaxies change over time. In visible light, we mostly see stars. But in infrared, we see the gas and dust that surround them. We see how galaxies pull in matter, how they form new stars, and how they collide with each other. We can track the structure of a galaxy from its bright center to its spiral arms. We can even see what happens when black holes feed on surrounding material. All of that activity glows in infrared. In some cases, infrared light lets us uncover things we didn't even know we were missing. There are entire groups of galaxies hidden behind thick walls of dust that only become visible when seen in infrared. Some of them are among the oldest structures in the universe. These hidden galaxies help fill in the gaps of how everything formed. They explain how stars gathered, how matter clumped together, and how the early universe changed into the one we see now. For many scientists, the most exciting part is that infrared can show us things we weren't even looking for. That's because it sees the universe in a way we never could before. It picks up whispers of light that have been traveling for billions of years. It captures the glow of things just beginning to form. With Webb's eyes tuned to this heat, we now have a way to listen to the oldest stories in the universe. A mirror forged for the early cosmos. JWST's mirror is the largest ever built for a space telescope. It's more than 6.5 meters wide, which means it can gather a huge amount of light from faraway stars and galaxies. When it comes to telescopes, size matters. The larger the mirror, the more light it can catch. And the more light it catches, the more it can see. Instead of being one solid piece like Hubble's mirror, it's made of 18 separate segments, with each segment being made of a metal called beryllium. Beryllium is light but strong, and it doesn't change shape easily, even in extreme cold. That's important because Webb operates in the freezing temperatures of deep space. Each mirror segment is coated with a thin layer of gold. Gold is very good at reflecting infrared light, which is what Webb is designed to see. Even though the gold layer is incredibly thin, just a few atoms thick, it makes a big difference. It helps bounce the faintest bits of heat back toward the telescope's sensors, where they can be turned into pictures. To make sure the mirror worked as a single unit, engineers gave each segment a set of small motors. These motors can move the segments forward and backward, tilt them slightly, or even bend them a tiny bit to correct for any imperfections. Once all 18 segments are perfectly aligned, they behave like a single smooth mirror. It's not just distant galaxies that benefit from the mirror's size. Closer objects, like planets around other stars, also become easier to see. With more light, Webb can take sharper pictures. It can spot details that were invisible before, like the details of an exoplanet's atmosphere. This can help scientists figure out whether a planet might be able to support life. Even objects inside our own solar system are seen more clearly. The mirror allows Webb to take detailed images of icy moons, dark asteroids, and the outer edges of the solar system. Some of these places are so cold and far away that they barely give off any light at all. But with such a powerful mirror, even those dim signals can be turned into valuable data. Building such a mirror wasn't easy. It took years of planning, testing, and careful design. One of the challenges was making sure all 18 segments worked together. On Earth, gravity can pull things out of shape. But in space, those effects disappear. Engineers had to design the mirror to change shape slightly once it reached orbit. They also had to design systems that would let them adjust the mirror remotely, using tiny motors and sensors that respond to changes in light. The way light bounces off the mirror tells Webb where each segment is aimed. Special sensors track how light is focused and help adjust the mirror in real time. It's a bit like tuning a piano, only instead of sound, it's adjusting for the shape and focus of light itself. The goal is to bring all the light to a single point, creating a sharp, clear image. This level of control is what makes the telescope so powerful. Even the smallest movements matter. A shift as small as a few nanometers, less than the width of a virus, can make a difference. That's how precise the system had to be. And yet it worked. After years of preparation and careful setup in space, the mirror came together as planned. The first test images sent back from Webb showed that everything was aligned. The pictures were not only clear, they were deeper and more detailed than anything seen before. If the universe is stranger than we thought, what comes next for science? Science has always lived in the space between certainty and surprise. It builds itself on patterns, on repeated results, on what can be measured and tested. But every so often, a moment comes when the data pushes back. A discovery appears that doesn't belong in the framework we've been using. In the past, these moments have brought both confusion and excitement. And now, with the JWST, we may be standing in one of those moments again. It's in the gap between expectation and observation that science grows, but it doesn't grow easily. When data conflicts with theory, the first response is usually caution. Scientists check their instruments, they double-check the math, they look for simpler explanations, errors in calibration, effects from nearby stars, confusion between overlapping signals. Most of the time, these checks resolve the issue, but sometimes they don't. Sometimes the odd result holds up. That's where we seem to be now with JWST. The telescope has delivered a stream of results that multiple research teams have confirmed, and the more we look, the more those patterns stand out. At this point, it's becoming harder to argue that all of it is just chance or mistake. So what happens next? In science, when the model doesn't match reality, the model has to change. That's the hard part. It means rethinking the ideas that have worked well until now. It means going back to the equations, the assumptions, the basic structure of how we believe the universe works. That means adjusting the foundation without making the whole building collapse. One of the first steps is to ask better questions. Each question becomes a path of investigation. New simulations are run, new math is explored. Old ideas that were once set aside are brought back out and tested again. This is the beginning of what some call a paradigm shift. It's when the rules of the game are being rewritten. It doesn't happen in a single paper or from a single scientist. It happens through a slow, collective process. Teams all over the world work on different parts of the puzzle. Some push the edges of theory. Others focus on new observations. Over time, a new picture starts to take shape. One of the biggest challenges in times like this is figuring out how far to go. It's easy to jump to big, bold claims, but good science takes a steady hand. Scientists are trained to be skeptical, even of their own ideas, especially of their own ideas. So they take small steps. They test and retest. They argue and debate. It's how real progress happens. In the past, revolutions in science have often followed the arrival of new tools. Galileo's telescope, Newton's mathematics, Einstein's theory, the particle accelerators that revealed the quantum world. Each of these shifted the way we thought about reality, and each one came with growing pains. Ideas had to be dropped, others had to be added. Some scientists resisted, others embraced the change. But the truth didn't care about opinions, it simply waited to be understood. JWST might be a similar kind of tool. Its clarity and depth allow us to see things in a new light, literally and figuratively. And that light is pointing to regions where physics and cosmology might need to evolve. These are not small questions. They touch on the nature of space, time, matter, energy, and existence itself. They reach beyond astronomy into physics, philosophy, and even how we define reality. But they also start with data, with light from distant galaxies gathered by a cold telescope parked far from Earth. That light is the signal. It's what drives all of this forward. JWST is a mirror held up to our understanding of the universe. And right now, that mirror is showing us something new. What do you make of Webb's discoveries? Sound off in the comments below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.